Everything all set for the micro conference today? Jörg? He's going ready to get coffee before he starts. Well, James is here. If there's any issue, talk to James. Fun.
Yeah, I'll be sticking around.
Okay, I'm just bouncing through all the micro conference to see if everything's all set. Bye.
So good morning and good afternoon. Welcome to the Confidential Computing Microconference. This is the first one at Linux Plumbers, and I'm really happy about all the submissions that I got. And I think we are going to have some great discussions. By the way, can anybody hear me?
Yes, we can hear you.
Just fine.
Great, thanks. So next, I want to thank our sponsors of this conference. Without the sponsors, the conference would not have been possible. First of all, the diamond sponsor, Facebook, but also the platinum sponsor, IBM, and our gold sponsors, ARM and Microsoft, and the silver sponsors, AWS, Netflix, and Red Hat, and of course, the speaker gift sponsor, Collabora. So with that being said, I think we get started with the, sorry, I forgot the t-shirt sponsor, VMware, another one, and the Linux Foundation for providing the conference services, which is pretty important for an online conference. So with that, I think we can get started and dive into our first discussion about TDX live migration. Ray, would you enable your camera, and you should be a presenter now.
So, okay. You will use the slides I uploaded. So I want to be able to share my own here, right? Can you hear me? Hello?
Say that again, please.
You can hear my voice, right?
Yes.
Okay. So my name is Wei, and I'm from Intel. So I'm working on various virtualization related project. So for this one, I'm going to give a high-level introduction for this TDX now migration. I just had an introduction of this topic in KVM forum a couple of days ago. So some of you may already seen this one. But for the presentation here, I will just give the high-level overview first, and then go into some detailed discussions. So I will reuse these slides here. So first, we can review the TDX working model. So with the TDX supported on Intel Sephiroth and Laton CPUs, so we have a new execution mode added to the CPU called the sim mode. So which is split into sim root mode and sim non-root mode. So this one is pretty much like the VMX root mode and the non-root mode. So with the difference here is that with the sim root mode and non-root mode, we are able to run the TD guest. So the TD guest runs in the sim non-root mode. So it is different from the VMX non-root mode, which is the legacy VM case. So because now the hypervisor, so the QEMU and the KVM gets removed from the TCP, so they are not able to access the TD memory. So I list those states here, like the TD shared memory, it remains accessible. So for the TD private memory, so it's not accessible. And also for the TD vCPU state, they are not accessible. So because of this isolation, that KVM doesn't have direct access to the TD states, but it assists the TDX module to manage those TD states. For example, for the secure EPT management, so the KVM still owns the memory allocation, so it gets the memory from the host memory management and then give the page to the TDX module to build this as secure EPT. So KVM talks to this TDX module through those SIM calls. So there are a couple of SIM calls exposed for the KVM to use. So probably for this slide, I will skip this one. So I will directly give a high-level overview of this TDX non-migration framework. So here, as you can see here on the source side, we have a source QEMU. So see, this is the source, the TD guest. It needs to be migrated. And on the destination side, we also have the dest QEMU, which is the dest TD guest, which is launched when we want to do migration. And on both the source and destination side, we need to boot a special TD called Migo TD. So this TD is a service TD. So it assists the non-migration process of the guest TD. So its responsibility is to do a compatibility check and security attestation to ensure that the destination side environment is secure to migrate, and also ensure the environment is migratable. So it also has another responsibility is to generate a migration key. So the migration key is used throughout the migration process. So the key is set to the TDX module. So the TDX module receives this key. So when KVM asks for the private page to migrate, so the TDX module will do the encryption and then give the encrypted memory page to KVM, and then KVM delivers this page to QEMU. Then QEMU send it to the destination side. So we can have a check on more details of MigoTD, and I will have some deep dive discussion about MigoTD today. So for MigoTD, it's a service TD, as I mentioned, and it performs the basic job of migration policy evaluation and the migration key setup. And it talks to the TDX module using the TD core. And also, it doesn't need to have any communication with the guest TD. So guest TD is a lot aware of this MigoTD. And when migration starts, the VMM will bind it to the guest TD that needs to be migrated. So for one MigoTD, we can have it support multiple guest TDs at the same time. Like if we have like 6 or 10 guest TDs want to be migrated at the same time, in this case, we can just boot one MigoTD to support all of those guest TDs to migrate. So finally, it's the MigoTD is a part of TCP, so it's included in the guest TD's attestation. So it ensures the MigoTD is runs something that's expected to run. So there is a special case for the MigoTD communication. So as you can see here, the source MigoTD and destination MigoTD needs to set up a secure channel. So here is the TLS connection. So this secure channel is to securely transfer the migration key. So the key, so those channel needs to go to the VMM and then go to the host network stack and then to the leak all the way to the destination side. So the socket here is a relaying entity which relays message sent from the MigoTD. So it's a special guest MigoTD. So and then relay the message to the host kernel network stack. So this channel here is actually unsecure. So we did to set up the TLS communication to send this key. So there is a communication between the MigoTD and the host. So it's a guest to host communication. So for this communication, we design a VSOC transport here. So we have two choices here. One is to use the existing volatile VSOC, and another one is to use a TDVP VM core. So this is a special VM core from the guest to host. So we wanted to design a new communication channel using the VSOC protocol. And lastly, so I will open more discussion about the MigoTD communication, and after I finish the basic introduction. So for the MigoTD, it's vendor specific. So for Intel here, we will provide a reference design and a Rust-based implementation. but the cloud vendors can design their own MicroTD to support the migration. So they can even, so for our basic design, we don't implement any operating system inside the MicroTD. So it's a bare metal implementation. So if the cloud vendors want, they can implement their own, even put a Linux-based MicroTD. But in general, Linux-based MicroTD may be too large and too heavy. So I'm not going to deep dive into these details because I want to leave more time for the discussion later. So here as you see that we needed to transfer the migration data from source to destination. So there are lots of data needs to be transferred from TDX module to QEMU migration thread, which then send the data, encrypted data to the network and all the way down to the destination side. So here I build some kind of shared memory, so which is shared between the migration thread and the QEMU side. So in the QEMU side, I actually implemented a KVM device-based emulation. So this is the kind of the logical and the interface to the from KVM to TDX module, and this emulated KVM device, it creates the shared memory. So the shared memory includes the MBMD buffer and the payload buffer and the MAC list and the GP list. So when QEMU migration thread receives, it checks the bitmap and find a dirty page and finds that there it is, for example, it's a private page. So it sends a request through this device FD to KVM side migration device. And then the migration device will use SIM calls like export page. So it's a SIM call exposed from TDX module. So to export the data, then TDX module will use the encryption key, which was set by the MicroTD in the pre-migration stage, and then encrypt that data and put the encrypted data in the migration buffer, which is given by the KVM device. And also it creates some kind of header. So it's called MBMD, which is the migration bundle metadata here. And also for each page, like it supports multiple pages to be exported with one SIM call, export SIM call. So for example, we can have 16 pages in the list, and each page is encrypted, and each page is has a MAC calculated by TDX module and filled in the MAC list buffer here, and also a GP list. So each GP corresponds to a page in the green buffer here. So basically, we use shared memory to export those data. This is the framework. So I'm not going to present the implementation details. So here so the discussion I want to open here is the first one is for the MicroTD communication. As I mentioned that we currently have two choices here. Actually, we are not finalized which one to use, and we want to collect more feedbacks either from the community and from the customers. Some of us here prefer to use what have we SOC, and some of us prefer to use VM core. So for the reason for what have we SOC is that it has some advantages to use. And the first one is it's mature. For what have we SOC, it's mature. It's already been in upstream for many years, and the design is mature. And there are some existing utilities, like in this picture, I mentioned the socket here. So this socket, it already supports the AFVSOC, and it has been verified that it works with what have we SOC. But the disadvantage is that what have we SOC is KVM specific. So like on Hyper-V and on VMware, they have their own vSOC devices. Like Hyper-V have their Hyper-V style vSOC, and the VMware has the VMCI vSock. So the design is different from Virtio. So if we support Virtio vSock, so for the VMware guest, we may need to support the VMCI vSock driver in that VMware MicroTD. So we need to change something and conditionally compile the vSock device driver inside the MicroTD. So there are people who want to support VM core based vSock transporter. The advantage is that it's VMM agnostic, but in fact that even it's the design from design point of view, it's VMM agnostic, but from the implementation point of view, either Hyper-V or VMware or KVM, all of those hypervisors need to implement the backend, the device side backend on their own. So even the design is shared. But for the MicroTD side, they can only have the same driver following the design. So that's the advantage of the VM core-based vSock transport. But the big disadvantage here, and also my concern, is that it could finally be a reinvention of Virtio vSock. Like we may need to build the same shared rings for packet transmission. So for this one, it's the disadvantage. So this is the first topic I want to bring for discussion and see if there are any feedbacks from you guys here, or if you follow the thing I introduced.
Yeah, I mean, I would say that the main disadvantage of using vSock is that it might be difficult to do by a non-KVM hypervisor. Other than that, I think vSock is a great choice.
Yeah, actually, our option here is the VM core-based vSock or the existing Virtio-based vSock.
Yeah, but the problem is if you have other hypervisors, let's say somebody wants to do Xen or something else, yeah, they might need to implement Virtio first, or you might end up with something different for every hypervisor. So that's a disadvantage, I would say, of Virtio, that is somewhat KVM specific. Even though that's not true. I mean, there's some other hypervisors which have Virtio, but there are lots of hypervisors which don't have Virtio. Yeah.
Hey, Andy. So what part of Virtio is coming through in your implementation here? As somebody said, right, vSock is implemented on Hyper-V as well. So if you're only using the AFV, the address family for vSock, is that not enough here, or?
Yeah, I mean, but there might be still differences, even like say on Hyper-V KY, right? It's not.
I'm asking, what part of Virtio is coming through in your interface boundaries here that we can't simply use our implementation of vSock here.
Well, I don't know.
Okay.
Yeah, so if we choose to use the VM core-based vSock, we also need to add the backend implementation in different hypervisors. Like either Hyper-V or VMware, they need to implement their own, add the own implementations to their hypervisor. So like if I'm a Hyper-V developer, I may think that I already have a Hyper-V style vSock. So what's the value to add a new vSock here? So that might be a question as well.
Right. So assuming that if Hyper-V were to use this tech that you have here, we have to assume that I have all the backends for the various front-end services we have. So if I want to use vSock, I can expect to have the VSP for vSock on the host side. But anyway, I don't want to derail this discussion, but yeah, I'm curious to understand what other aspects of Virtio implementation of vSock is percolating through these interfaces that makes it tied to Vertio.
Seems not 10 minutes left, so probably I can. Any more comments on this topic?
Yeah, I have one. Right at the bottom, you say Intel provides a reference design, but the cloud vendor is supposed to do it all.
So somehow the voice wasn't clear to me. I didn't hear that clear.
At the bottom of this, you say Intel provides a reference design. You say the MIG-TD is vendor specific, and that vendor seems to mean cloud vendor, right? Are you expecting every cloud vendor to write their own? Because in open source, we'd rather receive it from somebody else.
Yes, cloud vendors, they can implement their own, but they need to public their own implementation and make that reproducible and can be checked, can be verified.
Why do they each have to do their own if they're all going to be public? Wouldn't it be better to have one open source implementation then?
They can implement their MicroTD and publish their code on some public website, for example, and people can just rebuild that MicroTD and generate the hash. So we will have a hash included in the guest TD.
I understand the attestation piece. So they need to write their own migration TD and then publish it so everybody can see it. But why then do we have to have lots of different implementations per cloud? Why not just one open source implementation, since it all has to be open source anyway, that everybody can trust and that everybody's verified?
Just to make it flexible in case like cloud vendors, they wanted to add their own policy evaluation. For example, they wanted to evaluate in their environment whether that's migratable or not migratable. So they may need their
wait. Policy does not belong to the cloud service provider in this. Surely it belongs to the guest owner. Only they should be able to allow or not allow the migration, because otherwise they can be tricked into migrating to a node that is unencrypted or something.
I'm not sure if I get that, but you know the one of the responsibility of MicroTD is to do this policy evaluation, right? For example, if the vendor have some physical machines like in different countries, and those countries might have some restriction to do the migration, so they may define their own policy.
Right. Wait a minute, that's not a cloud vendor policy, that's a guest policy. Guests may decide they don't want their data migrating to different geographies. Cloud vendors are totally agnostic to what happens in their data center. If we wish to prevent migration between two data centers, we could do it from the outside. We don't really care about
I think the discussion is essentially who owns the TCP. Is it the cloud vendor? Because if the service TD is provided by the cloud vendor, then the cloud vendor is in the TCP, right? But is that the intention? Because
who owns the TCP is different from who sets the policy. Yeah. Policy should definitely be a guest thing. It should not be a cloud vendor thing. If it's a cloud vendor thing, we can trick the policy and use it to extract the data.
That's okay, Jim, because all that I think they're saying is that you can provide a TD, migration TD, that offloads the validation to the guest owner. And that makes you happy for your.
So, Andy, I think it would be useful to really write down exactly what is the threat model that you're trying to address here and who's to be trusted, because we don't want the guest to trust anything that the host is providing. When I say host, I mean the infrastructure provider. Unless they choose to, right? There should be a model where the guest doesn't trust anything outside of the guest. I think that's what James was saying as well.
I think that one model that we eventually probably need is so that when, for example, that in a case where who owns the trust is So you have like likely an operating system provider, like an USB, for example, like a Linux distributor, and that the guest has to trust the Linux system distributor, right, for the guest and so on. But probably they also have to supply anything that's also trusted by the guest, yeah. So so for a given cloud, so they, for example, they would need to provide the service CD. And they probably also need to provide the guest firmware and things like this, yeah. So and anything that's like in the TCP of the guest would probably need to come from some trusted entity, which is probably that provider, yeah. So at some point, I think you need a model where the service CD comes together with the Linux distribution, so that you can, let's say, you trust Red Hat or you trust Ubuntu or trust somebody like this, then it all comes from the same party.
So I think perhaps another way of phrasing this question is, how does the guest specify what kind of migration TD measurement it trusts, or how does that happen? How do we pin the migration TD that we trust?
So the migration TD actually has some like a UUID and some attributes. So all of those things are calculated into a hash, and that hash is included in the report that is asked by the guest TD to generate the code. So the code is for the attestation. So there are some info about the MicroTD to ensure that's the right MicroTD that's going to be running.
Okay, so basically the guest TD has full control over what kind of mic TD attestations it wants to accept. Am I understanding it correctly?
Not the control actually. It checks. So it checks which MicroTD is going to be bound. Like even when the guest gets booted, the MicroTD is not booted, but we have a pre-bound interface, which do some pre-bound of the MicroTD that's going to be bound. So later when the MicroTD gets booted, so when migration starts, the VMM starts the MicroTD, and the MicroTD has to be the one that's already be pre-bound to the guest when the guest gets booted. So there is some kind of identity of this MicroTD. It has to match to the TD that's of the hash, which has already been included in the guest TD. When the guest TD boots, it do the attestation, including of the hash, but the hash corresponds to some kind of identity to this MicroTD. So that can be changed.
I see. So basically the guest TD has control over what mic TD measurement it trusts.
Yes, some kind of measurement.
Thank you.
Okay, I actually have another topic I want to discuss, but I'm not sure if I have time left. Actually, that one is not specific to TDX. It's also common to the SZVLAN migration. So I want to discuss about the data structure used to record the private and guest page. I saw the SZV patches from Ashi, if I pronounce his name correct. So that he's using that the region list, which uses some shared region list. So it's a address range to record if that page is private or not. And also another option is to use bitmap. So there are some advantages of using bitmap and using that shared region. So for the advantage of using bitmap is that it's simple and it's more performant. And the memory consumption is determined because it's proportional to the guest RAM size. For example, for 1 gig guest RAM, it needs like a 32 KB bitmap. But the disadvantage is that the guest with the huge memory size may require large bitmap size. Like if we have a huge guest like 1 TB, it requires 32 megabytes memory for bitmap. And there is a solution that I found from upstream. The discussion is that we can do guest memory donation. I think that's a good solution to do that. So the advantage of the
I think we discussed about that quite a bit on online discussions, and I think the basic thought process was that the bitmap probably is going to take a lot of memory and going to be very sparsely populated compared to probably just an interval list or just a kind of a linked list of regions, because the guess is mostly going to be private memory, right, rather than shared memory, so or unencrypted memory. So probably the linked list looked like a much better solution compared to a large bitmap, which is dependent on the guess RAM size, and also probably is going to be, as I mentioned, going to be very minimally populated. But I have some notes on it during my discussion, so we can probably continue that discussion at that time.
Okay.
Yeah, okay. So I think it's time to wrap that up and move to Ashish's discussion about live migration on SMP and SCV. So let's see. Ashish. So Ashish, it's your turn.
Can you hear me?
Yes, I can hear you.
Okay. So hi, this is my name is Ashish Kalra. I'm a software system design engineer at AMD. This is a discussion on live migration of confidential guests, but it's probably going to be a lot more discussion on SCV specific things, because that's the platform I work with. So as we have generally been talking about it at this conference and at KVM forum, that the confidential guests or the guests are encrypted, so you can't simply copy the ciphertext between machines to migrate a VM. It's going to be encrypted with that VM's key, so transporting that to another VM with a different encryption key is not going to work. What basically AMD Safe key management API provides is a lot of functions, kind of firmware calls, which support this kind of migration, where we have commands like where we basically start and basically establish an encryption context using PSP. PSP is our security processor, so it's the AMD SP or the PSP is the security processor. So we basically have commands like send start and receive start, which basically establish an encryption context between the source and target side. It's also sets up a migration key, which is kind of encrypted and returned back to the hypervisor. It's encrypted, and then the hypervisor basically sends it across to the other side, to the target side. And then there are specific commands like specifically like send update data and receive update data, which is basically used to send the ciphertext data between the two VMs, the source and the target side. So it's typically where the first part of the send update command data command basically decrypts the guest VM data using the guest specific VM encryption key, and then encrypts it with the migration key. On the other side, and then the ciphertext data is basically transmitted. And then
So the payload in transit, is that encrypted with the customer key, or is that infrastructure key that's used to transport?
It's a migration key. It's a transport encryption key or the migration key on which the data.
And who owns that key? Is that a customer key or no?
Who owns the?
And where do you get that key from? Is that something the customer can have a say on, or is that something owned by the provider of the infrastructure?
It's owned by the provider. It's basically generated through the AMD security processor.
Okay. And it's going to be common key across all migrations happening in the.
No, it's an ephemeral key.
Okay. Thank you.
And so on the other side, so it's basically the receive of data command, which is then re-encrypts basically decrypts the data with the encryption key, migration encryption key, and then re-encrypts with the VM encryption key of the target side. So this is the generic way it works, how migration works on the AMD SED platform. We have kind of two proposals for it. One is basically the AMD secure-based processor-based migration, which is the migration I talked about, which is the PSP-based migration. And as I mentioned, uses the pages are imported and exported like with the migration key. This is a slow migration path because it's basically uses the AMD PSP, which is kind of a bandwidth. There is like that's a bottleneck in this particular case. The other is a fast migration, or which is in-guest migration or guest-assisted migration, where there's basically a migration helper. As of now, there's some kind of a prototype implementation from IBM Research, which was also talked about in the KVM forum, and which implements the migration helper as part of the VM firmware, that is the OVMF portion. And here, it basically is the migration handler runs in a separate mirror VM, which is a clone of the primary VM, and shares the memory context and the encryption context with the primary VM. So if you look at the earlier basic model which I talked about, is the slow migration. The fast migration path does not use any of these PSP commands. Doesn't use the send update data, receive update data, send start, receive start to start the encryption context. It basically has components which are basically two migration handlers, a source and the destination migration handler, which basically is launched on both on the source and target side separately, and also tested separately. And they basically have some kind of a synchronization, kind of a symmetric key implementation, which a more complex key implementation where the key is generated by the guest owner and basically inserted into the VMs after the test session is done, after the launch measurement is done of the particular VM. So that works in a slightly different manner than us. Also, it doesn't use the PSP, so it's not restricted by the bandwidth issues which we have with the slow migration path. And probably also because it's an in-guest migration, so doesn't need to do decryption and encryption of the VM specific path, just the transportation path. So also kind of makes it faster in that sense. I'm not going to talk much about the fast migration paths already discussed as part of the KVM forum. But there are some specific components here which kind of depend on that too. So we are going to kind of talk about that part specifically. These are the state of patches for the slow migration path. The hypervisor host Linux patches got merged in version 5.14. The guest kernel and the guest API patches are still in the discussion. I posted last version 6. Similarly, there is OVMF patches version 7, which are also posted upstream. And then QEMU patches were recently posted. They are more like an RFC patch right now. And there's been some discussion on it. There's been discussions on all three components. There's specific parts which I just want to continue here so that we can probably have some consensus of what we want to go ahead and do. And the guest-assisted migration is more like an RFC right now. So it has portions where there is a mirror VM part of QEMU, which was posted upstream. And then there are the OVMF and the QEMU specific parts of the fast migration, which is, again, under discussion right now. So just looking at some basic things which have been discussed and which already exist. So what we basically have is the guest kernel and the OVMF making a specific hypercall, which is basically informing about the page encryption status tracking. So this is a KVM HCMap GPA bench hypercall. The host patches for this are already there as part of kernel 5.14. And this goes into KVM, and then we have an exit path for this. So it's basically passed through, and there's a KVM exit hypercall exit code, and it passes through to QEMU. And then QEMU basically, at that point, we basically have a structure where, this is a structure which I was kind of mentioning earlier in the Intel TDX discussion, that we have a shared region list which basically tracks the guest page status, page encryption status. So it's basically GPA star GPN kind of list, interval list. And what we discussed mostly during the patches when they were being upstreamed, and we had long discussions on it, is it's probably better to have a shared region list than the bitmap, because bitmap, one thing would be it's kind of dependent on the guest memory size, the guest RAM size. So it could be for a large, huge guest page size kind of thing. It could be a very a large bitmap allocation, and which will be mostly sparsely populated, because again, it's the most of the guests will be just having ranges of a small range of memory which is shared, and most of the other memory, which is like MMIO memory or things which are used for DMA or something like that, or there are specific pages which need to be kept as decrypted, and most of the other regions of memory are going to be private pages, so which are encrypted. So we don't need to really maintain that kind of thing, and the bitmap remains mostly unpopulated. So it could also cause things like denial of service issues, which we discussed, because of the large page allocation or something, or maybe just the number of hypercalls coming in and just resizing the page allocation bitmap again and again. So that's other thoughts we had. So we decided on something like a shared region list, which is more like an interval list, just containing the ranges of memory which are unencrypted or shared between by the guest, and both the guest kernel and the guest firmware makes these calls and then exits out to QEMU to actually populate or basically insert elements into the disk, or when the pages become encrypted again, they could be just removed from this. This portion of QEMU is still under discussion. It's the patches have been posted, but so there are things to talk on this, and then see if this the implementation looks good or not. So yeah, the next slide basically talks about how does the whole encryption process works. Again, it's based on the slow migration logic, but then portions of this. So as I mentioned, this the page encryption status tracking is also used by the fast migration handler. So this is something which is common between both the slow and the fast migration path. So this is something which needs to be put in concrete, in that sense, that because it's going to be used by both migration proposals which we have, and maybe also specifically for Intel TDX in long term. So talking about this migration path, so what we basically have is on the QEMU side, whenever there is it's the migration, this is the RAM migration part for sending and receiving encrypted pages. So it basically checks if the GFN is encrypted. It basically consults the guest share region list, which is already part of the QEMU. So it doesn't need to make any specific in-calls into the kernel or up-calls into the kernel. It basically just can track that data, which is directly available to it. And then what I added was adding, there is already a confidential guest memory support class, and I basically added some memory encryption ops as part of that. This is something, again, which needs to be discussed and decided upon if it's the right place to put this encryption ops or not in this particular structure. This is a kind of a structure which was a confidential guest support class, which was added for confidential guests only. So it probably made sense to add the specific ops for migration as part of this particular class in QEMU. And then it uses it basically makes an outgoing page call at this point, which gets into an IOCTL into the kernel, and then there's a send update data command, which I talked about earlier. It goes to the PSP, gets the encrypted data. It's transported to the other side, the target VM, on which this is just the pre-copy path. So the pre-copy path at target VM basically loads the incoming page, again makes an IOCTL call, gets into the receive of data command, and the PSP basically at that particular point decrypts the data and basically re-encrypts it and puts it in part of the guest RAM. So that's how the path works. All of this is something which the guest share region list, as I mentioned again, and probably mention it again, that this is going to be something which remains common between the slow and the fast migration paths which we have. So just continuing with this further, So what we have, these are, so I just, part of this discussion now just comes to things which we have and things which we want to discuss as part of this microconference and see if we could have some thoughts on what we really want to do as far as the guest kernel and the guest API support patches, which, as I mentioned, are still, which are upstream but still under discussion. So what we basically have are some hypercalls which are made earlier than the apply alternative section part, which is executed as part of setup arc. And these alternative hypercalls, especially, which, as I mentioned, specifically to decrypt the guest kernel sections like DSS decrypted, and then there are specific pages which need to be set as decrypted. And these are made before the apply alternatives call. So there's a specific issue with this, that the default hypercall on x86 platform maps to a VM call, and we specifically want this to in case of Intel, in case of AMD, it has to be the VMM call, which is the hypercall instruction. So we really cannot use the default hypercall infrastructure, and we want to use apply alternatives to set it to VMM call later on. But it cannot be, the specific issue comes when we have to make these early hypercalls, which are pre-alternative. So at that time, VM call has not been patched to VMM call. So there has to be some kind of an early pre-alternative hypercall interface. And what I have been talking about is that we basically have, most of the hypercalls are made through an interface which is like early set memory decrypted encrypted interface, which in turn invokes paravert ops. And what my thought process has been that the early set memory interfaces can be mapped to a specific paravert op, say like notify page encryption status change, and that gets mapped to a specific servo TDX specific hypercall. I think so. This is one thing I wanted to discuss. Let me just complete this thing, and we can just come back to this if one need. The other part of things are how do we basically support and detect the line migration feature. So this is kind of a three-way handshake between the guest kernel, the host user, and the host KVM side, the QEMU side, the guest kernel, and the OVMF portion. So it's the host basically enables the migration feature, and then OVMF detects it and sets up a runtime variable, a UEFI runtime variable for it, and the guest kernel then at the KVM initialization point, the init platform part of the guest kernel basically checks if it's under EFI or not under EFI, and accordingly checks for the UEFI variable support, and then we have a custom MSR which basically indicates that the guest has enabled line migration feature. As of now, so this is another thing which is still under discussion, probably needs to have more discussion on this. Again, the migration, the MSR handling is implemented using the MSR filtering on QEMU, which probably has been a recent support which has been added, and again gets into QEMU to actually do the MSR handling and then enabling the line migration feature and connecting to the QEMU migration code at that particular point. So as I mentioned earlier, as part of the slides, the QEMU support basically adds a new confidential guest memory encryption ops. These are the kind of ops currently which we support. So we have things where we are basically saving the outgoing page, and we also have the shared region list, which I mentioned. This basically has the tracking for the guest page encryption, and option and the support to basically migrate the shared region list. And similarly, there is the option to load the shared region list. And so the confidential guest support part, which is already there, has the new memory encryption ops added to it. Again, it's something which is probably something to be discussed about. So as I mentioned, this is the EDK side of things. So we've been talking about the three-way negotiation feature between hypervisor, guest kernel, and the guest kernel, which I kind of discussed about. And so yeah, I think that's basically concludes my general slides. Now I've been wanting to talk about these couple of features which we discussed about. So one has been about how to support the guest kernel and the guest API thing. The other thing has been the feature enabling part, which is the three-way handshake, and then also, if possible, how does the QEMU support look like? Is this the right place to add the encryption ops? So these are, I think, the kind of three main discussions to talk about, because these are things which probably hold the patches right now for upstreaming. So yeah, so I think so. So just coming to the first part is the guest kernel and guest API support. So we've been having discussions on it. But does anybody have any, anybody wants to just take up the discussion on this or have thoughts on this, which we can discuss further on?
So, from the point of view of the QEMU migration maintainership, the challenge I have is that we have these 2 or 3 different schemes that are all incomplete. So we have the choice between the PSP slow migration, which is too slow to be practical, and we have IBM's guest assisted stuff that doesn't yet have some of the features in that we need, like the encryption and the ES support. And then we have the TDX stuff coming as well. So the challenge from the QEMU side is to get the bits in that are common and then try and figure out what we can do to get a practical solution rather than 3 entirely separate things.
Okay. But what? So there are still some specific common paths, right? Which I mentioned, like the guest page encryption status tracking, probably the three-way handshake. These things are probably going to. I understand that slow migration doesn't seem to be a very a long-term path because it's really slow, and that's something which we know. So what about the common paths like the guest encryption status tracking? This is something which the fast migration path also uses, right? So we need to have some consensus on supporting them or at least having them available. So what's your thoughts on that?
Yeah, I mean,
as I mentioned, like these the specific things like okay, this is already the part of the host interface right now. It's already being upstreamed in host, so it's going to remain pretty common for that part. So, but then we have portions which are exiting out to QEMU side, and then this is something which we maintain right now. But then this is something which is going to be used and varied by the fast migration path also. So we should probably have some consensus on this support and see if this part can be upstream so that at least the fast migration part can also use it accordingly.
I actually checked your previous discussion about the shared region list, and but I saw the discussion was focusing on how to optimize this, but there wasn't any discussion about the difference between the shared region list and the bitmaps. So I'm not sure if everybody has already agreed to use this or. I can.
Yeah, I think let me give a little bit historical, right? When I started, so this is Brajesh. When I started working on live migration, we took the bitmap approach, exactly what way you have been saying, is we went with the bitmap approach, but there were many discussion upstream on the KVM mailing list. And most of the feedback at that point was, if you have a large guest or if you're ballooning a guest, then you will get into all these situation where you're expanding the bitmaps and stuff. So the recommendation at that point was, hey, why not just explore other alternatives, the region list, where we know 99% of the guest memory space is actually a private memory space. So there is no need to maintain that data on the hypervisor, only maintain the data for the shared region. So yeah, if you are interested, I think I can dig up and find you and send you the link for a discussion, but they all are KVM mailing list.
Actually, I already checked those links and the discussions, but I don't think there are lots of discussion talking about the difference. I understand what you mentioned there. So, but from design point of view, I think it really depends on the guest behavior to decide whether it's shared or private. Guest, like a malicious guest, can set each page as private and the next page as shared, and in that case, the shared region list will be much more larger. The size will be much more larger than bitmap. For the bitmap, its advantage is that the size is determined when the guest is.
But if you start ballooning the guest, right? If you start
even with ballooning, the guest its memory is determined when the guest boots, right? Like if we have an 8 gig guest gets booted, so the bitmap size is determined. So when we do ballooning, we actually just balloon the memory from inside the guest, like the balloon driver, like will take like a 4 gig, but it doesn't affect the bitmap, right? We want to increase the bitmap size, right? The bitmap size is determined when the guest boots.
But okay.
But there
maybe I'm missing something.
There could be other cases, right, where the guest size can increase, right? There could be like the hot plug maybe or something. It's not just boot time; it could be a runtime things also, right?
The hot plug is performed by the hypervisor side, like the QEMU. It's not determined by the guest. So like if the cloud vendor, they can operate the QMP command to hot plug memory. So that's not decided by the guest.
I guess the confusion over here is in case of earlier patches, the bitmap was maintained by KVM in the kernel, but I think what you are saying is bitmap should be maintained in the QEMU. Is this my correct?
No. It's maintained by KVM, but we can have an option to have this memory be allocated from the guest. Like if the bitmap, like it takes like 1 meg, for example, so we can have the guest to delete one megabytes memory for this bitmap. So in QEMU side, it's pretty easy to do. Like if the guest size is like it's 16 gig, so we just use 16 gig minus one megabytes. So then the guest RAM gets deducted a little bit from this bitmap.
Yeah, I think I have seen cases where OVMF BIOS basically clears some of the pages, like some MMIO region makes a shared like 48-bit address space, so really high number. Even they are not part of the guest memory space to begin with. That could be like high MMIO addresses or stuff, and OVMF actually goes and says, hey, I want to mark this entire top of 64 gig as a shared memory region. So you will start getting a request from a guest which says he has high number GPA, make it as a shared, and now you don't have memory if you are working with the bitmap, because your guest might have allocated memory only for a guest RAM. It may not have accounted for other unknown GPA yet.
Do you mean that the memory used by OVMF is outside of the range of the guest RAM size?
Yes. So those are one of the thing in SCV. I don't know about the TDX, but one of the thing in SCV is all the MMIO memory that need to be mapped shared, and the MMIO's memory. Some of the thing OVMF access are not part of the guest memory space. They're very high numbers.
I think that's a great example actually.
We can
really big, right?
Yeah, I think we can take this a discussion online, and I can point you some of the codes.
Yeah, probably. I think I can open a discussion even on the mailing list to have an offline discussion on this one. To list, I can list all the advantages and the disadvantages.
Okay.
Okay, by the way, for the SCVNet migration, I saw you have 2 proposals. Do you have any performance number to compare? Because you call it a fast. How fast is it compared to the Snow migration? Do you have any initial?
But I think there is really it's more like an RFC right now. So there are really, I don't think there are any real numbers for fast migration right now, or even if there are, it's with IBM research guys. Probably they are the right people to talk about it. A slow migration is quite slow, so that much we know.
Yeah, a pure slow migration is very slow if you're using the PSP for every page. There is the work that IBM's doing that's a pure ingest that doesn't use the PSP at all. And then there's talks also of like a hybrid approach where you use the PSP to migrate just like the helper, the migration helper, and then you proceed with fast migration from within the guest.
With the migration helper, is it multi-processing support? Like if we have multi-FT support in QEMU, would it be workable to support that? Like,
Yeah.
Okay. This is an interesting discussion, but I suggest we continue this offline or in one of the hack rooms later after the conference. I'd like to move on to the next session, which is TDX Linux support. Andy, you're now presenter.
Okay. Okay. Thank you. Hope you can hear me? Okay. So I'm talking about the TDX guest, and this is just a high-level overview because I mean there's actually a lot of topics, but some of them are fairly complicated. There are lots of people who worked on it. So so me and Satya and Kirill and Elena and other people like Shani Sebastian, Isaku, Chao, Casey, and others. Yeah. And the original port was actually done by Sean Christopherson. Okay, next slide, please.
I think you can switch. I think you can switch yourself. You are a presenter.
Yeah. Let's see how to do that. Oops, no. How do I do that?
Does it work?
There should be a button down in the middle.
I don't see the button. Somehow it's not there.
Oh yeah, right.
No, I see.
Somehow.
Yeah, thank you. Okay, so this is just a quick overview. I assume most people have already seen something like this. But we have like the TDX enabled Linux guest, and this is it has to be enabled using TD calls for power virtualization. And there's also the TDVF. This is the guest BIOS. This is based on EDK2, at least in the reference implementation. This is also in the trusted guest. And then we have the TDX module, which is a module supplied by Intel, which implements like it's trusted and implements the trusted policy essentially. that like sits between the hypervisor like KVM or other hypervisors and the guest. Yeah, and then we of course have host Linux, and then there's an underlying CPU. Mm-hmm. And the guest uses TD calls to do all the communication and also shared memory if needed. Yeah, and we using the TD calls to implement lots of operations like MSRs, MMIO, port.io, CPUID, most CPUID, and a few other things. Yeah, and at least in the initial implementation, the IOs for virt.io like on KVM, but it can be also different for other hypervisors. Yeah, this is the basic overview. Okay. Yeah, just I wanted to talk a little about a few topics that we are working on. The one thing is we are looking at performance. What we're seeing on the performance front is exits that go to the host, they have more overhead than in a classic hypervisor. And this is simply because they go through the TDX module, and essentially it's essentially two exits. Yeah, the TDX module, you have an exit to the TDX module, and then you have from the TDX module you have another exit to the host, and obviously this is a little bit more expensive. So in general, any optimizations that reduce exits are good. Yeah, so that we've been looking at various things. For example, one thing we noticed is is when you just run something CPU intensive, like which doesn't do a lot of I/O, then you have a little bit of more overhead. And we think this is related simply to the TSC deadline MS-Arbeit. Because every time you have a time interrupt there, it has to reprogram the timer there. So we are thinking actually maybe we can use a periodic mode to reduce that. It would only help when you don't have any other timers, but yeah, this might be a possible solution. But in general, yeah, for performance, we are looking at reducing exits as much as possible. Yeah. Yeah. And then another issue we ran into, we see this quite a bit on I/O intensive workloads, is because for us every I/O has to go for software I/O TLB. So because it needs to go to shared memory, and we don't want to set memory shared and unshared all the time. That would be too expensive. So instead we have this large pre-allocated buffer in the software I/O TLB, which has been already shared with the host. So in every I/O which has to be shared with the host goes through that buffer. Yeah? And so we're just using the legacy software I/O TLB system, which has been traditionally or just used for devices which are less than 4 GB. And it turns out, because traditionally the software utility system was never performance critical, because it was only used like as a fallback for slow devices, like for USB or things where people don't really care that much about performance. Yeah, but now what we're seeing is, so for example, especially when you have a couple of vCPUs, like 8 or 16, there's some really bad problems. So we had cases where you spent like 20% of the time in spin locks, because software I/O TLB has a single spin lock. So yeah, so we are working on patches in the work to split up the spin locks. So essentially partition the software I/O TLB into areas which have their own spin lock and then reduce this problem that they're all contending on the same lock. Yes.
So as you know, on the Hyper-V side, we had our own implementation of bounce buffering for communication with the host. And then based on the feedback we got from Christoph and others, we're moving towards using the exact same framework that you have for VirtIO today, the software I/O TLB framework for bounce buffering. And we saw about 40% drop in performance between what we had before and going into this built-in shared buffer infrastructure you have for software I/O TLB. So as you're looking at optimizing this path, at least the goal for Microsoft is to get to where we were with our own custom bounce buffering scheme. Is that also something you guys are interested in, or are you happy with where you are?
No, like I said, no, we want to be better. Yeah. So I think we are hoping that once we with our patches, with our optimizations, that it shouldn't give you the 40% regression that you're seeing. Yeah. So yeah. And I suspect that a large part of this 40% were probably the spin lock problems, especially when you have plenty of vCPUs. But the other problem is we also saw is it makes very inefficient use of the memory, because it cycles through the software TLB all the time. It's not a LIFO, it's a FIFO, not a LIFO, and this is very inefficient for caches. So there was also, we have a patch, I think it has been already posted, to change the software TLB to reuse the buffers as quickly as possible, which is much better for the working set. Yeah. So yeah, KY, we are hoping that with our patches, hopefully this will fix this problem. Yeah. But I mean, maybe there's a more tuning possible. We have to see. Yeah, so there might be a little bit more work needed to generally optimize this, because just traditionally it hasn't been optimized. Yeah.
Yep. Thank you, Andy.
Okay. Yeah. Okay. Then lazy accept. So Kirill unfortunately is not here. So there's another problem we have is that, and I think that's also shared with other implementations. So all the memory that's used in the guest, it has to be accepted by the guest first. And today, like in the initial implementation, this was all done in the firmware, yeah, so that the firmware accepted all the memory. But this turned out this can be really slow, depending on how much memory you have in the guests. It's fairly expensive to do this, and you end up with like relatively long delays in at boot, and this is not acceptable, especially for use cases who want to spin up guests very quickly, like for containers and so on. Yeah. Yeah. So what we are looking at is lazy accept, and I mean there was already quite a lot of discussion on this on Linux kernel and how to do it. And I think Kirill already posted some patches for lazy accept. So essentially, what we are what we currently have in our patches is so there is a change to UEFI that some memory can be declared as not accepted yet, or I think it's got. I think it has a different name, but anyways, it's basically not accepted memory. So the parts of the memory, a small part it comes out of the UEFI firmware, which is already accepted. But then in the memory map, the most of the memory is actually not accepted. And then we in the decompressor, we accept the memory that we need. We're doing this at a 2 megabyte granulity, so we always accepting a 2 megabyte range or 2 megabyte sizes. And then we are maintaining a bitmap, which is also again 2 megabyte. And yeah, every time we accept something, we set it in the bitmap, and this bitmap is then passed on from the decompressor through the boot protocol to the main kernel, and so on. Yeah, and then the reason why we need this bitmap is because the kernel shouldn't accept anything twice, because this would be potentially a security risk. Because if you accept something twice, you might zero it, and I think, and my understanding is on AMD it causes even other problems. Yeah, so that the bitmap essentially is to keep track of has been already accepted. The way it's also implemented is that so once we are in the main kernel and the mem map is up, there's also like an offline bit. We are aliasing it an existing struct page bit. And then we have hooks into the page allocator, which if something is already is not accepted yet or is offline, then we can accept it when we allocate the page. Yeah, and this also prevents. So there's no need for any exceptions. It's possible for in the TDX architecture to have an exception, like when you touch some memory which hasn't been accepted yet, and handle it. But the way we implemented it is this shouldn't be needed. In fact, we don't want it, yeah, because it causes the so-called system call gap. Yeah, yeah. So everything is they're managed in 2 megabyte, but the offline bit on the for the mem map is obviously at the 4K level, because the struct page is a 4K level. And actually, there's an open issue right now. This is still needs to be figured out. How to pass the bitmap to KExec, because the problem is that we have is that shared memory needs a different handling. And right now our bitmap is only at 2 megabyte, but the shared memory is not let's say aligned to 2 megabytes, so it can be at 4K chunks. So we probably need some other mechanism to tell the next kernel, if we do KExec, that the shared memory. Okay, I got muted somehow. Yeah, so we right. So the bitmap. Yeah, so we have this problem that the right, the shared memory needs to be handled especially, but we cannot express it in the bitmap because there's 2 megabyte granulity. So we still need to find some mechanism to pass the shared memory also to the KExec kernel, so that it can be handled correctly. That's why currently KExec is not supported yet, but we hope to fix this at some point. Yeah.
Hi, Andy. Do we know how much how many 4K pages are usually unaccepted, or how many pages which are not 2M aligned?
Do you mean how many are shared?
Yeah.
Yeah,
I mean, we need to handle that over somehow, right? So that information is important.
Yeah, so right now we don't track it. Like I mean, no, in theory it's in the page tables. In theory you could find in the page tables, but there's no count. I think there's no count or anything. But we probably need to add some kind of infrastructure to track what has been shared or not. But actually, it's actually not a lot of dynamic, because the way our setup works is that the only thing that's really shared is the software utility, which is like a 64 megabyte chunk. And then we only have a couple of small things which are normally shared, like a few communication things and a few MMIO regions. But it's actually mostly the 64 megabyte plus a couple of pages essentially. So it's not actually that big a deal. It's not that it's like a lot of memory or a lot of different regions, but it still has to be done somehow. Yeah. Mm-hmm. Okay.
So all of this stuff sounds like a lot of hoops to jump through, with like passing down bitmaps all the way through the whole kernel boot up phase. Is that actually necessary? Like, why don't we just go and say we always have a 1 gigabyte region that is declared as memory, and then everything above that 1 gigabyte range just gets declared as needs to be accepted memory, and then the kernel just can boot within that 1 gig, and everything beyond that it just accepts lazily or installs lazily as soon as it uses it.
So I think it would be actually okay for TDX, but it was apparently a showstopper for AMD. We had this discussion because on TDX it would be okay because it has to be tracked during a single when the main kernel is running. Because otherwise the hypervisor could replace some memory regions with zeros, which would be a security attack. But when you actually KEX-SIGing, then it's usually okay to replace stuff with zeros, yeah, at least one time, yeah. So in TDX it would be acceptable, I think. But so we had this discussion on this kernel, but it turned out that on AMD it causes, I think Jörg pointed out, it causes some other problems. So we have to really track everything, right, Jörg?
Yes.
Yeah.
You must, on AMD, you must make sure that you don't accept twice. So everything else would be a security issue, and you have to track this information across KXX.
Okay, let's take those two conversations separately. Okay, let's try to just talk about booting and KEX-SIGing as separate things. I think you already concluded that for KEX-SIG you need to have additional information where you actually have to describe on a 4K granularity where pages are shared and so on and so forth. Like KEX-SIG is a completely different beast. But just for booting, like how far along are you with the patches to do the 2 meg dances and pass that along the whole boot chain?
We have the full patches have been posted. Yeah, the Kirill has a patch kit. It's on the Linux kernel. So we have full patches. The only thing we are missing essentially is the KEX-SIG handling. And I think there was recently they found a bug that sometimes we have a sometimes when depending on the memory layout we have a crash. We still need to fix that, but I mean, in principle, the patches are already implemented, and they're actually not that bad. You can take a look at them. I can post a link. Yeah. So yeah. So it sounds complicated, but it's not that complicated. Yeah.
And the problem with pre-accepting, like say 1 gig of memory, is that your address space layer randomization will then put the kernel within this first gigabyte of memory, and then you lose some bits of the randomization. So what you need is support for unaccepted memory in the decompressor, which actually does the physical placement of the kernel in the memory. And if you have that, you can also go and say, hey, everything besides what the BIOS tells you is unaccepted, and go ahead and accept it as you need it. So
fair enough. Yep.
So
thanks.
Is there any reason not to accept more than 2 meg when we get the hint that pages need to be accepted? The reason why I'm bringing this is in case of SNP, when we do the page state change, basically when we accept the memory, there is 2-step process. One is exit to the hypervisor to add the page in the RMP. And when we exit to the hypervisor, we can actually batch up a lot of entries. So we can batch up more than 2 meg. We can batch up all the way up to 500. So we can say, okay, take one exit, go and add the RMP entry for up to 500 megabytes.
Yeah, I mean, you could do that if you want, but I mean, just a bitmap is at 2 megabyte, but you can do it in larger chunks. However, the problem is if you do it in too large chunks, you might end up with too much latency, because often people care about a latency during runtime, like, tail latencies. So I suspect if you do it too large, then there will be problems. For us, our API is currently only up to 2 megabyte, and there's no batching at this point. So we are kind of restricted to megabyte.
And remember that the current patches are doing this in the page allocator. So you can go do 100 terabytes at once, but somebody's waiting on a page to come back for that to happen. So you don't want to make it too long, is what Andy's saying.
Right. I think there might also be spin lock issues. Yeah. So you have to be careful with too long latencies. Yeah. Yeah. Okay. Any other thoughts or comments on this one? Okay. Then next slide. Security. So first I should add, Elena has a separate, much longer talk on this, which is going much more detailed at the Linux Security Summit. Yeah, but I'm just giving you like a high-level overview. What we're doing. So this is actually one of the largest challenges we have, or the most work. Yeah. So in general, I mean, the problem we have is that the guest is protected, like its memory is protected and its registers are protected. But it still has all these touch points with the host. Yeah, so it communicates for MMIO, for MSR, for some MSRs, not for all of them, and for shared memory, for virt.io, and a couple other things. Yeah, so and essentially, because the host is untrusted, this is essentially I think of it like it's like being a server on a hostile internet. Yeah, so you have some ports open and somebody can attack you. Yeah, so and you have to make sure that. I mean, if you are unlucky and the code, let's say, has a buffer overflow which passes some data, then they could use that to let's say find some primitive in your code and then actually read all the memory. So all the memory encryption and memory protection wouldn't help you if they can basically take over you using these communication points. Yeah. So it's really important that we secure this. Yeah. So we have to. Right, we have to make sure, and the challenge is also that traditionally Linux always has trusted the underlying hardware, yeah. So that because essentially from the point of view of the kernel, this is all hardware, yeah, and none of this code really has been written to assume that the underlying hardware is trying to attack you or be malicious and so on. Yeah, I should add there's a little bit of prior art here for on the client side. Because they have this problem with malicious USB or Thunderbolt devices, yeah. So there was a little bit of work there for hardening some drivers, but not very much, yeah. And a lot of the stuff we are hardening. I think we actually looked at it. We built some tools to look for other places. I mean, there are really thousands, or in some cases tens of thousands of places in the kernel which can potentially communicate with the host and process some data, and so it's really frightening somewhat. Yeah. Anyways, but our strategy for this is first disabling as much code as possible. So we have quite a few patches to just get rid, because a lot of communication bots are actually not needed. They're like for some obscure feature which is not virtualized, or we don't care about. So we're actually disabling a lot of code to just make sure that it doesn't even run, so we don't need to audit it or harden it. For that, I mean, the biggest problem, of course, is all the drivers, yeah. And obviously, I mean, Linux has like hundreds of thousands of drivers, like millions of lines of code. There's no way you can harden all of this, yeah. And there's an obvious attack where, like a malicious hypervisor which controls the PCI config space could find some driver which has a buffer overflow and then just present the PCID of that device, and then get UDEV to load the driver, and then exploit the driver, and then exploit the guest. Yeah. So what we, but of course it doesn't make sense because most of these drivers we don't care about. They're never used usefully in a guest, right? We only want virt.io and maybe some other drivers for, let's say, VM bus or something, but not like the vast majority or 99.9% of the drivers. Yeah. So what we been working on is we have a device filtering framework, and at the device layer, at this central driver layer, but essentially we have an allow list, or a very small list of drivers, which is mostly virt.io, or pretty much only virt.io, and then only drivers which have been actually audited and hardened, they get allowed. They get allowed in the list, and everything else cannot even probe. Yeah. So we prevented that the driver model to load. Yeah. So yeah, there was already like an initial patch posted there by Satya, but the initial version Greg didn't like. He wanted also more unification with the existing work in the USB stack, which also has a concept of an authorized device, which is used a bit similar, that you have only audited USB devices to prevent USB attacks. So actually, Satya has been reworking the patches, and we have been reworking the patches several times, and I think we are getting ready to repost them soon with the new version. Is that right, Satya?
Yeah.
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 Right. Yeah.
The patches are near completion, so we'll be posting it.
Yeah. So we have we have a new version which is uses pretty similar infrastructure as the existing USB. So essentially, it generalizes the existing USB authorized concept, and based on that one, we have our allow list we can inject when we are running in TDX, and then and then this prevents like the vast majority of drivers to load. Yeah.
Hey, Andy, so this particular framework you're talking about, is it simply an allow list where you go and statically add new drivers that you think you trust?
Yeah, currently we kind of have a static list for TDX, but we also added a command line option for like extending that list.
Yeah, Kev, I should add, the idea is not to prevent anybody from, I mean, if you have a driver which you want to support, you're happy to do that. But it's just, what we want you to do is to audit and harden it first, and then add it to the allow list. Yeah?
Right. So
obviously
you would ordinate first, harden the driver first before adding it to the list. Yes.
Mm-hmm. Right. Yeah. So right. This is this. But I should add there are a couple more problems. So first, there are various things which are outside the driver model. For example, in the early x86 code, there's some early PCI, and there are quirks and other things. So we have quite a few patches which are mostly pretty simple. It's just a few lines. If we are in the in the confidential guest mode, then don't do this. So we have some other patches for things which are outside the standard device model. There are some other issues. For example, because the way a normal driver loads is, so there's an init function which is called by init call or by module init, and in many cases, like especially with legacy drivers, those they sometimes do already communication with the host, or they try to do something like they probe something, they IO remap something, they probe something. And this would be in principle already attack points, because in principle there could be already buffer overflow in this early code, and this unfortunately cannot be prevented by the driver model because it doesn't really control the module init, or doesn't control the init calls. So what we also have, you have some extra defense mechanisms. So one, for example, for the IO ports, we have a hard-coded allow list. We expect this is probably because IO ports are really legacy, so there's not much need for extending this. And for IO remap, because for us the IO remap only works when it's set to shared. So if you have an IO remap region, you have to set to shared. And originally we had a policy where every IO remap was automatically shared. But now we switch. I mean, we switched to that you have to actually declare the IO map to be shared. And it turned out for us it was only like two places in the kernel which we actually need to change there, and everything else we don't set to shared, and this actually the communication doesn't work. In fact, it's a little bit ugly, unfortunately, because what happens is that you upload on the host level, because when you do an MMIO there, the host notices it and notices that I cannot handle it, and then it has to essentially kill the guests. So this is not very nice error handling, but because we expect this shouldn't really happen in practice, right? This is or if it happens, it's a security attack. So we think you're okay with it. But I should add, we also have we have command line options to override this. So if somebody wants to actually do IO remap, or let's say add more drivers, so there are command line options to add more drivers to the allow list, and command line options to override the policy of making IO remap shared. So it's possible to do that, but it has some security risk, because if you make all the IO remap shared, then then everything that's in the init call and it might be called and it hasn't been audited might be attackable. So there,
Okay, so I think we are up for a break now. So to finish this discussion, I would like to mention that tomorrow in the Testing and Fuzzing Micro Conference, there's a session about device driver fuzzing. So everybody who's interested in that can attend that as well. Device driver fuzzing is about finding actually the bugs in device drivers and hardening them. And with that, we are going into a 10-minute break.
Thank you.
And yeah, thank you, Andy, and see you in 10 minutes. Okay, I hope everyone is back. So let's go to our next topic, debug support for confidential guests. Ashish, you are now our presenter.
Okay, can you hear me?
Yes, I can hear you.
Yeah, so so the next thing we're going to discuss is debug support for confidential guests. Again, the discussion is generally more about specific to SCV, the platform I work in, but there are specific TDX patches on top of the SCV patches, so I would probably also bring it up during the flow, during one of the flow charts down here. So it's as we already have been discussing, the encrypted guest, the VM has its memory, and maybe in our case only after SCV ES, the register context also encrypted by specific technologies like AMD SCV or Intel TDX. And because it's encrypted, it breaks down QEMU's built-in debugging features, as it cannot directly do guest memory access, specifically things like memcopy from the host virtual address or something. So we've been, this discussion is generally more about implementing a basic framework and a common XLSIC implementation to say handle encrypted guest memory read writes, and specifically to support QEMU's built-in debugging features like the monitor command or the GDB stub. So again, talking about, so this discussion is generally more about the QEMU debug support required for confidential VMs or guests. And again, the AMD security processor specifically has specific key management APIs like which basically allows you to decrypt or encrypt the guest memory. So you have debug, decrypt, and debug encrypt PSP commands, which allow decryption and encryption of guest pages. We do have a guest policy, which also can be set in case we want the VM to be debugged. So this is the kind of implementation. These are very implementation-specific notes on the QEMU side about things which have been done as part of the patches. So the memtx attributes structure has been a new specific bit field added to indicate that this memory access is from a debugger. This is the basic first patch, and then on the very top level interface, you have something like CPU memory read write debug, which is the main interface function called whenever there is a virtual memory access, a guest virtual memory access from QEMU side. So this is something which needs to be overloaded with some vendor specific assist or hook for debug access to guest memory. So we added a new memory debug ops hook, new memory debug ops structure, which basically hooks into this CPU memory read write debug interface, and also the physical memory side of debug interfaces to basically allow and basically do read writes to guest memory which is encrypted. And so the main functions are the read and write side functions or the callbacks, and there's a PTE mask which is specific to SCV for page table walking. There's a little bit more chat on it later on. So if you see CPU memory read write debug kind of has been modified. It sets the memory TX attributes accordingly, and instead of making direct calls to address, so this is the address CPU memory read write debug is the QEMU's main function used for the address space read writes. So instead of making direct calls to address space read and write functions, it now goes through this memory debug ops structure which we added, and makes specific callbacks to those read and write commands instead of making direct address space read write calls. So that's one of the main things it does. On top of this, the memory region itself, the QEMU memory region itself needs to be overloaded with, because it currently uses a memcopy to, which I talked about earlier, memcopy from HVA to do specific guest memory read writes. So again, there is a new structure added, memory region RAM read-write ops, which basically has just 2 callbacks. And in the memory region now basically includes this this structure as RAM debug ops. So this is the change from the memory region side of things. So how does this flow for, how does this API flow for SEV guest? I have a generic slide for it on how on the Intel patches on top of this. But then what we see is just SEV right now, and we will see what the generic patches. So you have the main virtual interface, virtual memory read function called, and it maps into the memory debug ops callback, which basically makes an SEV specific call. And then we added some read-write debug helpers. So you basically internally invoke the address space read debug, which now instead of making a direct call to memory, which so earlier this was just a mem copy code, but now this specific read-write debug helper checks if it's the debugging, it's a debug access, and you have the callbacks for that, and invokes the memory region specific callbacks on top of that. So that's why you need an address space hook and a memory region hook, which work in a coordinated way to finally call back into SEV or a TDX specific interface to read or write guest memory. In case of SEV, this would just map to, as we see in the next slide, it maps to basically an IOCTL going into the KVM side, which will basically use the SEV API, which I talked about earlier, encrypt or debug decrypt to basically encrypt or decrypt the guest memory at that particular point. So we do added, so these are just the virtual memory side of things. For the physical memory read-write APIs, there's been new specific interface functions added. So they have been like all the CPU physical memory read-write debugs, and then there's been the reading or a long or a keyword specific interface. So which again internally invokes the new memory debug op structure. So the changes are you need to make specific changes in the QEMU code whenever it's accessing guest memory. For example, if there's a TLB info thing which will be invoked as part of the GDB stub info or the monitor command, it will, instead of making a CPU physical memory read, now it calls into CPU physical memory read debug. So that's where one of these APIs get used accordingly. In the guest page table walk, again, there is specific hooks needed because when you are basically going to read the page table entry, you will have the C bit set in case of the SEV guest. So you will we basically have to mask that C bit to get the right or the true physical address. And we again go through the debug ops. This is the PTE mask callback, which I had. Which we had just kind of seen earlier. So this one. So this basically gets the right C bit or the right C bit position in case of for SEV guests, and then the mask is applied accordingly. Similarly, the page table walk continues for PDs and PTs accordingly. There's a specific handler to do MMU guest MMU lookup of the page table walker. I have basically have a translate callback for it, but right now it's not currently used. Instead of using that translate function or the callback, we basically just override the CPU class page attribute debug handler to point to the SEV specific callback to do the page table walking. This is more of a top level diagram, just shows the complete relationship between the APIs and interface being added. It kind of is, again, this is basically based on top of the Intel patches on top of the SEV, the Intel patches just were pushed on top of the SEV patches. So if you see from a top level point of view, this is the one which is doing the page table walking. It internally invokes the physical read-write debug functions. They go through the debug ops. For a normal guest, they just get mapped into address space, read and write ROM, which will internally then invoke memory region and just do a mem copy or something. But in case of an encrypted guest, they get into debug ops, and then if it's an encrypted guest, they get mapped into the specific helpers, read, debug, and write debug helpers. They go through. They basically get the memory region, and then the memory region. It's because the attributes are set, and the RAM debug ops callback is available. It calls back into KVM encrypted guest read write memory functions, which will map to either set IOCTL for SEV and KVM IOCTLs for TDX guests. And this is for the physical side of things. For the virtual side, the similar code path is used. It's the CPU memory read write debug is the main function for all virtual memory access. So again, just goes through the same path from top level, from the address space handler to the memory region handler, and then goes into specific IOCTL paths, which will invoke the PSP to, in case of SEV, invoke the PSP to get decrypt and encrypt the guest memory specifically. And so, this is generally about the memory side of things. But as I mentioned, that, and probably that's also true for TDX, that SEV ES also encrypts the register state, and which the CPU register state. So that is still that's a limitation of this of the whole interface currently, because specifically in case of SEV, there is no way to directly get or there is no safe SEV key management API, which basically allows you to debug or decrypt the register state in that sense. So this is something which which needs to be explored, and this currently is a limitation. So accessing CPU register state as part of the QEMU debugging interface, or even doing device accesses. So you might have issues while for QEMU device emulation that device access may not work because the register state is encrypted. So these are things which are still open-ended. We just need to see what can be done for this. Probably needs some kind of guest awareness. Is there a possible way to probably do a virtual debug or trap or debug interrupt injection at that time? And then does it need some kind of VC handler, or the GHCP is a specific SEV structure for guest and host communication. So this does need some kind of guest awareness, where the guest needs to basically supply back, get the decrypted register state back as to the QEMU side or the host side using the GHCP structure, and then that's where the QEMU can pick it up and do these specific things which I talked about. So yeah, so this is these are patches as I mentioned have been submitted by us in the guys, and then Intel push the patches on top of that. So there's been a limited discussion on it. They are still kind of open-ended patches, and so the point here is to if there is anything which we can discuss about it right now here, or are there any general comments about it or any specific comments about it that we can probably discuss right now?
Hey Ashish.
Yeah.
Is there a chance to get the register state debugging feature before the memory debug ops? Because that's I consider pretty important for doing any ES development or SMP development.
Yeah, but as of now, there is like as I mentioned, there is no direct support for it in hardware, right? So this is completely an open-ended thing right now. The patches don't address this right now. So the
PSP can decrypt the register state, right? If debugging is enabled for the VM.
For Tom, you want to go ahead? Go ahead.
No, I was going to say, I mean, the problem that you run into is where do you if you're in debug handling or entering breakpoints, you're typically in the VC handler, right? So now it's the VC handler that has a PT reg struct, and it's those regs that are there that need to be communicated back to the debugger, right? So it's not that you'll be able to stop right on the instruction when you have, like in the case of ES, and then you have to take into account, okay, so how do you convince the guest? How does the guest ensure and is positive that debugging is actually allowed in his policy, and so we'd have to work something through there. I'm not sure that we have that capability under ES to be able to do that.
Yeah,
Maybe
but
under SMP we might be able to have like a guest command or something.
yeah, the guest needs to be aware that, or the guest needs the attestation report to know that it's being able to debug. But still, for some exits, or actually for all automatic exits, it would be useful to have the decryption when it is enabled in the policy. So what usually happens when I develop ES code and it crashes very early, then I get a shutdown or something like that, or it just stops executing.
Yeah, I mean,
because it ends up in some loop. So
yeah, I know that's kind of how I did a lot of debugging too. As long as it's an automatic exit, right, where you're not coming through the VC handler, right, then you will have the regs at that state, and then you could decrypt the VMSA at that point if the policy is set to allow that. I know both you and I use that quite a bit.
yeah, right. But it's still the out of tree debug patches, and it would be great to have something upstream, right?
Yeah, it might be something we could do that, as long as you're not in the VC handler. So if you do get a shutdown, you can look and see what your register state is. So I can work with Ashish on that when he gets back to the office here soon.
Okay, great.
Yeah. And I think with the CVES, another thing is, we may able to decrypt the VMSA, but we will not able to update the VMSA if somebody is using the GDB type of functionality to set the register values and stuff. Then that will not work with the CVES.
Right.
But I think with the SNP, we will not have those limitations. So.
Okay. So if there are no more questions, I think we can move on to the next session, which is running confidential containers. Samuel, you should be a presenter now. I can't hear you. No, still no audio. Samuel, maybe it works if you rejoin the room. So maybe to give Samuel some time to sort the audio out. Jacob, can we probably switch the talks because you are the next?
Yeah, we could. We could.
So Samuel can sort out the audio issues, and then we have his talk afterwards. I know that you prefer to be after Samuel, but yeah.
Yeah, this is unfortunate. It's okay. It's not the end of the world.
Okay.
I will
Then-
introduce some things that I thought he would introduce, but it doesn't matter, honestly.
Okay, then let me see where I have in the list. So you should be presenter now.
I'm presenter, right? And here's slides. Okay. Yeah. Hi. My name is Jakob Nauke. I work in cloud development for Linux and OpenShift on IBM Z and Linux One at IBM. And I want to talk a little about confidential computing on IBM Z with secure execution and the challenges that we're looking at, especially with confidential containers. And so, yeah, IBM Z and Linux One, or I might just say IBM Z through this talk, you may traditionally know as the mainframe, the ST90X architecture, and it is, among other things, used for Linux and Red Hat OpenShift workloads. And IBM Secure Execution for Linux is the hardware confidential computing backend that we have that's been introduced with the latest model Z15 in 2019. and it is always based on virtualization with Linux and KVM, so like SCV and TDX, and also protected execution facility on Power. It is always on virtualization level, so no application level. And the sole problem, or well, one problem at least, that these confidential computing technologies always need to solve is making sure that a workload really runs in a secured context. Like you have a supposedly secure domain at, I don't know, a cloud provider, and you want to I don't know, SSH into it. You want to make sure that they're really running what they're supposed to, or that they really running what you gave them, if you gave them something. Because if they could inject something, that would be an open door for malware, right? And the way that SCV and TDX achieve this is generally through attestation, pre-attestation or runtime attestation, and perhaps smaller encrypted key containers. Secure execution and also PEF go a slightly different route. They have a fully encrypted boot image that can house pretty much anything you want. And it's encrypted with an asymmetric key, or an asymmetric key that chain loads a symmetric key. And that asymmetric key is tied to the machine that you want to run on. So basically, based on serial number, you have a key, a public key to encrypt your boot image with. And that is basically the root of trust in running a secure execution guest. Only this machine could ever decrypt this image and therefore launch it. But the problem that you have to solve now is retrieving that private key for decryption, because if the hypervisor could just read it, then you haven't really gained anything. Then a rogue admin, hypothetical admin with root access could still get that key and do malicious things with it. And that's where what we call the ultravisor comes in. So the ultravisor is implemented in hardware and firmware. And when you boot a secure execution guest, the hypervisor will immediately reboot to the ultravisor. And that will be able to decrypt the secure image and will handle guest memory pages. And those will not be available to KVM or QEMU or other Linux processes. And I/O still remains visible, of course, also power consumption and scheduling. And so those should be encrypted. I/O should be encrypted, but register contents and memory contents are undumpable. So just to reiterate a little what the workflow would look like in classical secure execution, you need to bootstrap a Linux system on trusted IBM Z hardware, and that would use LUKS or some sort of disk encryption, because remember, I/O remains unprotected. And you would have a kernel and a command line and an init.rd, and you would put the key to that LUKS root FS into the init.rd. This may seem a bit counterintuitive, because now you're shipping the root FS with the key to it. But what you do is you create this secure image. So that's with checksums. And now, because only the machine that you used, whose key you used here, can decrypt this. This is the way you know that the workload is really secured. And this may be fine if you want to run a normal secure execution virtual machine. This may be fine, but you might want to run something else. You might want to run containers. And the challenges that we have there, I want to talk about a little. So where I primarily work is the Kata containers community, sorry, that Samuel will also talk about. And Kata containers, basically, we run our pods as tiny VMs. So it's OCI compatible. You can use it with containerd and the likes. but the actual containers run in tiny VMs that are based on different hypervisors, and we have a kata component on the host that talks to containerd, or that is talked to by containerd, and that can talk to a component in the guest that we call the agent, and that can launch one or more containers. So yes, there's the sandbox. It has its own kernel and everything. And Kata containers slogan sort of is having the speed of containers, but the security of VMs, because it's as fast as virtualization is on your platform, which is generally pretty good. And launch times are a little slower than a traditional runC container, but they're reasonably fast, or actually very fast for a VM, like ballpark of 1 second, or maybe even a little less. And you get the security guarantees of VMs. You get some things that you don't necessarily get with C groups and namespaces. So isolating guests so they can't possibly break out is one use case, but another is using confidential computing technologies that are based on virtualization, obviously, like secure execution. This is also a community effort. Very little of this is my own work, but we in the Kata community, we're currently looking at enabling confidential computing technologies with this. So utilizing the hardware is one step. This is generally done for all major virtualization-based technologies, and locking down the agent so it doesn't just do anything that the host component, the runtime, tells it to. This is currently being looked at by Samuel, who I think will talk a little bit more about this. But one core problem that we want to solve with confidential containers is running an encrypted container image, because that might very well be what you want. You have a custom encrypted container image that probably contains some other secret that you use to connect to an API endpoint. And we will initially, or in current development, we are pulling this image upon creating a container. And the core problem you have to solve now is getting the key to decrypt it. And this is where SCV and TDX can use their various methods of attestation to receive a key at runtime. But which, or at least in later generation, SCV SMP can also use a runtime attestation to establish a secure channel to retrieve keys. But because secure execution and also PEF do not have attestation in that sense of the word, because they don't require attestation in that sense of the word, we can go, or I see currently, two slightly different routes that we may go. So the one approach is what I like to call the bake-in approach, where you would have an init RD with a Kata agent and an attestation agent, which is also a component that's being developed right now for attestation, but we will simply use it without it actually doing attestation, but simply using offline baked-in keys for decrypting containers or container images, which is very simple because it does not require any external component running at runtime, but it's not very flexible because you're stuck with the keys that you put in there, and when you want to re-roll these keys, you will have to build a new init RD. And the other is what I like to call the key fetch approach, which is going to be a little more akin to what SCV and TDX do, because they talk to a guest owner proxy at runtime, which has to run on trusted hardware and which can provide keys for container image decryption. And because it uses gRPC, we can simply secure that connection with TLS. So you, yes?
What's the role of the attestation agent in the bake-in approach?
Very little. Basically, because all the architectures are going to use the attestation agent, we will use it too, because then integration is easier. But what it will more or less do is it'll receive a container image that's going to be encrypted. This is also going to use OCI crypt, or OCI crypt Rust. And for retrieving the key, what it will normally do, or what it will do on SCV and TDX, is use their secure channels, and instead it will just read from a file or from an offline key, if that makes sense.
Yep.
Okay. And the key fetch approach, we will connect into an endpoint, but we will use a TLS certificate that will be baked in instead, which is a bit more flexible because you can now re-roll container image keys, and you will only need to redo that initRD when you need to renew the certificate and the key. So that's basically a substitute for runtime attestation. So about development, all the core hardware technologies are enabled. This bake-in approach is going to share some work with SEV, or first generation SEV, because that with its pre-attestation workflow, there will be some similarities. And I also want to work on the key fetch approach. And one other thing that I want to look into in the future is building these initRDs without requiring trusted IBM 0 Linux 1 hardware, because obviously it would be a bit more convenient if you could do that on commodity hardware, which is probably going to require some cross-building and or emulation. But I have yet to really look into that. So yeah, thank you for listening. Just quickly, so the trademark info is here. We can discuss other approaches if you think, or Kata's overall model, or more questions about secure execution, whichever you like. I also see there's something in the shared notes. Our TCB recovery work in a model where we just have a SNKDF pub key. I'm afraid I'm not familiar with all the abbreviations that you use there. I'm aware of TCB. Maybe you can speak up or edit them in.
Okay. Hello, can you hear me?
Yes.
Oh, sorry. So yeah, 1 second.
No worries.
I can cover this in a minute. Sorry.
Serial number. Yes. Okay. Thank you. Key derivation function. Yeah.
So the question is around TCB recovery, which is this process. So basically, if you discover a vulnerability in the microcode or in some lower level parts of your TCB, then in the case of Intel SGX, they have a specific process for basically upgrading the microcode, patching the vulnerability, and upgrading in a way which is visible in the attestation. So actually you can prove that the TCB is upgraded and safe. And then I guess the question is, how do you do this if you don't do attestation? And like how do you actually do recovery in cases of discovered vulnerabilities?
Okay. I do have to admit, I primarily work in Kata containers and its secure execution enablement. I think this is being looked at the moment, but I'm not entirely sure, I have to admit.
I see. Thanks.
Hi. I mean, I'm not an expert here either, but the key element, I think, to this is that because there is an aspect of image encryption, then there is the opportunity that suggests that any update could form the path of rolling keys and things like that. So if you have an encrypted image from a previous level of firmware, then you would be using potentially a different key to a later version of firmware. But I'm just guessing here, so don't quote me on it.
Okay, thank you, James.
Hey, Jacob, the ultra visor you talked about,
yes,
is that considered more secure only because it's a smaller surface area? What makes it more trusted than the hypervisor?
It's not operating system level. So it's hardware and firmware. You just make a call to it, and you cannot control it beyond its defined API, even as root user.
Right. So from a guest TCP perspective, that would be part of the guest TCP, and the guest can see what it is, and you're going to publish it openly, and the guest images come with that.
Sorry, I mean the guest image is built from. I mean, what you do with the guest image is you have a very normal Linux system basically, and you have a key that belongs to the machine, and you encrypt it, and the private half of that key can only be read by the ultravisor.
Yeah. Thank you.
All right. There are other questions. Samuel, would you be ready?
Can you hear me, Jacob?
Yes, we can hear you, Samuel. Oh, great.
Oh, great.
Technology. I'm gonna discuss the benefit of Safari versus Firefox on different operating systems. That seems to work.
Okay, let me just load your slides. So here we go. Oh, now you need to be a presenter too. Now you can switch slides.
Okay, cool. All right. So apologies for the audio hiccups. I'm going to talk about containers, and Jacob kind of touch upon it. And here I'm going to talk about confidential containers, and we call it confidential containers. It's one way of doing it, I guess. There are potential other models. The thing I'm going to present and the model and the architecture that we are working on is something that we do as part of the Kata containers project. So this is for now relying on the Kata container runtime. And because I don't assume everyone on the call knows the architecture, the Kubernetes architecture. I'm just going to give a very, very brief explanation on how things works with Kubernetes. And as a reminder, Kubernetes is the arguably most deployed container orchestration layer out there. And so when we talk about deploying containers, deploying confidential containers, we usually mean that in the Kubernetes context. So if you look at just a regular super high level Kubernetes node, you have at the top of this diagram something called kubelet, which is the Kubernetes agent. It's kind of the agent that receives the commands from the Kubernetes control plane, and it talks to a container runtime, containerd for those who are familiar with it, or CRI-O, are the two most deployed one. And then it calls into runc typically, and runc essentially creates a Kubernetes pod. And by Kubernetes pod, we really mean a set of processes running inside a set of namespaces, C groups, and various isolation layers. That's what makes a pod. A set of containers that are tightly coupled, logically coupled. And the important thing to note here is that they are running off container images that are deployed on the host and that are usually stored over an overlay FS partition. And each process can use a different container image and runs off a different container image typically. So that's the regular way of running a Kubernetes pod, containers in a Kubernetes environment. What we did with Kata containers is say we want to add an additional isolation layer. We want to add an isolation layer at the pod level that's going to be based on hardware virtualization. And for that, we essentially start a virtual machine, and that's going to be the pod. And inside of this virtual machine, we actually run the same set of processes that are going to be running out of the same container images than the previous diagram. Except here, those container images are going to be exported into the guest through, it used to be an IPFS. Fortunately, now we can use VirtIFS. But essentially, it's a power virtualized file system that exposes the container images from the host into the guest. So that's the Kata container model. We also have something important to note here is that we have the runtime on the host, the Kata containers runtime, talking back into the guest. There's a specific guest agent running for talking to the runtime. And the reason for doing so is because the kubelet and the overall Kubernetes control plane typically are going to want to control the pod and the containers that are running inside the pod. They're going to be executing some processes, additional processes in those containers. They're going to be getting some I/O. They're going to be signaling those processes and various different things. So we need to have a communication from the Kata container runtime into the agent in order to forward and basically transfer all those commands from the control plane. So that's the current model. And the thread model is it's basically trying to implement is really protect container to host and protect against container to host and inter containers at ag vectors. That's kind of the same model that the regular runc based, process based bare metal containers are building. It's just that it improves the thread model by adding an additional security layer. So with something like Kata containers, the barrier for escaping from the guests, from the container, from the pod, is higher. So what we're trying to do with confidential containers is expand this container thread model and really protect containers from the host itself. We want to remove the CSP from the trust boundary. And at the same time, we want to keep the container to host and the inter-container protection. So what we want to do is basically use confidential computing hardware. And there's already quite a few products out there that are proposing this, where you can run your Kubernetes node inside confidential computing context. And that's not what we're trying to do here. We're not trying to put an entire Kubernetes node inside a TD or an SCV VM. What we're trying to do is run each and every pod within its own confidential computing domain. So the boundary and the security boundary lives at the pod level, not at the node level with this approach. So if we go back to the Kata containers diagram, what we could do is basically add some magic layer, run on top of a confidential computing hardware, start the VM or the TD with in TDX context, and let's say we're done, but we are actually not done at all. So when we're running the pod inside a confidential computing context, the only thing we do and the only thing we provide in the containers and Kubernetes ecosystem is to encrypt the guest memory. So that's already an interesting use case that further protects the container to hosts and inter-containers attack vectors, but it really doesn't bring the confidential computing model to the container and Kubernetes ecosystem. Why? There are many points that we need to fix in order to do that. As I said, the container images, which is again really what the pod is going to run. The workload of a pod is the set of container images. It's not the guest image. It's not the guest kernel. It's not the guest agent. It really is contained on in those images. So if you leave the container images under the host control, then you're completely breaking the confidential computing model. There's also this nice VSOC channel that we use for communicating with the guest agent. If we keep it this way, essentially we leave a complete open door for the kubelet and the Kubernetes control plane to kind of drive what's happening inside the guest, and we don't want that neither. And last but not least, we don't really know what's booting if we don't test and verify. So in order to really implement something that is looking like confidential containers or confidential pods, we need to do a few things. We need to pull and keep the container images inside the guest. So it's a completely different model to what all the current Kubernetes deployments are assuming. We want to keep all the containers image inside the guest. We actually want to pull them inside the guest, not inside the host. So the host won't be able to see anything. We only want to use signed or encrypted container images. We want to test the guest. And by the guests, I mean anything from the firmware up to the guest agent. So the Kata containers agent, which is again the piece of software that's if you get here, the guest agent is the one responsible for actually spawning the processes that would run off the container images. So it's kind of a little reduced runtime running inside guest. And when we want to measure and test is everything up to the Kata agent. So we want to be able to measure and verify everything up to the Kata agents. And once we can verify that this is working, then that this is the right set of software component, then we can proceed and actually start pulling the container images and decrypting them, or at least verifying them. And to do that, we need to provision the guest with the container images keys, either for verifying or decrypting. And the last thing we want to be able to do is to restrict the exposed API. So the kubelet API, what I'm calling here the kubelet API, is essentially the set of commands that kubelet and the Kubernetes control plane can forward into the guest. We don't want to close everything. There are quite a few things that we can allow and keep, and we think we can keep the confidential computing thread model intact. But we do want to restrict a few of those commands and requests. So if you look at what we're putting in place, and again, this is what we want to present here. This is really much a work in progress. Out of all those components here, there's quite a few that are not ready yet. We're really actively working on this with people from different silicon vendors, different software vendors. We're all putting this together, so everything is open. Everything is ready for feedback and potential changes. But essentially, in the guest agent, now we're gonna be able to pull container images from any kind of registry. It doesn't have to be trusted, because we're gonna pull encrypted or at least signed images. So we're going to be able to pull and unpack those container images, which means that all the container image management layers that are currently living on the host, that are currently embedded in components like CRI or Containerd, have now in this model they have to be moved inside the guest as separate libraries. So there's a stream of efforts for kind of extracting those pieces into what we want to do are Rust crates for pulling, unpacking container images. which is the bulk of container image management. Once we pull an image, the next thing we need to do inside the guest is to decrypt or verify them. And to do that, we're using a component that's currently being worked on as well, but it's fairly advanced already. It's called OCI Crypt, which allows for calling into any kind of binary through an RPC mechanism. And here in that case, it's going to be the attestation agent. And the attestation agent is going to be responsible for provisioning the guest with keys. And to do that, it first needs to attest the agent, get a quote from for the whole guest's software stack, send that to the relying party, and if everything is verified as expected, get a set of wrapped keys back into the guest. Then the attestation would pass those keys back to the decryption layer, which will decrypt all the container image layers, which is something I didn't get into, but typically container images are very much are a set of layers added on top of each other, kind of a union FS. That's what overlay FS is doing. Once we decrypt all those layers, then the guest agent will be responsible for unpacking those layers, putting them together, mounting them in the right order, because it gets that information from the container image registry, and keep all those container image layers inside the guest. Now we have a model where the host no longer sees the container images, is no longer able to tamper with the container images or even the metadata associated with container image layers. So you wouldn't be able to force the guest and the pod into mounting different layers in different orders and kind of play with this in order to exploit the guest. So the host no longer sees the pod memory. It no longer sees the container images. What it still can do is send some specific commands to the guest in order to control it. And this is where we are adding another layer of protection in this VSOC-based API between Kata containers and a guest agent. And we're building and expanding the guest agent so that a guest owner can define which part of this API it wants to support. So as a guest owner, if you are saying, I actually don't want to forward any kind of IO back into Kubernetes, I'm just going to disable this. And if I don't want to exec anything from that Kubernetes is going to ask me to do, which is something that typically you wouldn't want to allow, you can also do that. Essentially, you can take the entire VSOC-based API and, as a guest owner, make business decision on which part of this API and which part of the Kubernetes API you want to support. That has large consequences on what set of Kubernetes workloads you're going to be able to support. Because by restricting this API between the host and the guest, you're kind of removing part of the container workloads that you are still able to support. So it really is, we believe, a business decision, and we're providing the hooks for defining the set of APIs, the endpoints that you want to support, and adding that as a configuration file that is going to be part of the measurement. So that's the model that we're proposing, that we are working on right now in the Kata containers community, and I think I'm basically getting into more details on what Jacob described in the previous presentation.
Yes, Samuel?
Yep. Okay, why?
If you can go back to the previous slide.
Sure.
So now the main reason we chose to keep the container images staged in the host was the assumption that perhaps there would be multiple containers that would spin up from the same set of images the host had already downloaded. So in the model that you have here, are we kind of trading off security with storage here?
That is true. That is, and this is one of the limits and restrictions that I'm calling out in the next slide, where basically the idea of being able to duplicate or not duplicate container images across containers is kind of reduced here, and the advantages of doing so is mitigated, I would say. What you can do, and this is why we are adding these ephemeral block devices. We want to be able to store, still store this container image on the host, encrypted. So we want to encrypt these ephemeral block devices with, for example, a tenant specific key. So you would be able to, per tenant, share your encrypted images and say the same tenant running the same, I don't know, NGINX encrypted images with some added value on top of this could be able to share those ephemeral block devices between tenants. But
So
that would be
Samuel,
where the deduplication would stop, I would say. Yeah, go ahead.
so since the container images are already immutable, what is the additional advantage we get in encrypting it?
Well, they're immutable if you're. I mean, you can run a Kubernetes pod with mutable container images. Kubernetes can ask for a pod with writable layers on top of the container.
Right. So at least the portions that are immutable, the lower layers that are supposed to be shared across containers, perhaps we could
If
treat them
they're immutable, if you trust the host not to poke around with them.
Yes.
If you're not trusting the host can modify them.
You could attest the integrity of the immutable image independently in the guest, no matter where it is staged and placed.
Well, I mean, obviously the container image could contain secrets, confidential things that you don't want the host to be looking at. So, and I mean, it's not only about the testing, it's about making sure that the host does not see what your container images are containing. So there's another model that we've been discussed, and this is where the host would be able to control and download encrypted images. The thing with the encrypted, the container images specification for encryption is that the images layers themselves are encrypted, but the metadata that actually is used for mounting those layers on top of each other and describing the order of how you're going to mount them is something that is not encrypted. So there's still a hole there where the host could decide that it can tamper with this metadata and force the guest into mounting different layers in orders that are not expected to be mounted. You're still able to test your container images, but since the host will be able to modify this metadata, you still have a window there where the guest could mount them in the wrong order. And
it feels like you could have some intermediates. So, for example, you could have a DM integrity based base layer, OS base layer image with your whole OS on it, and you could pass that image into all of your guests.
Yep.
And then you could have the overlays on top of that encrypted, and the layering done inside the guests.
Where would the metadata live in that model? The metadata
When you say metadata, which part do you mean of the metadata?
So a container image is a set of layers.
Yeah.
Each layers, but it's also a set of files describing how those layers are living and are mounting on top of each other.
So that would be well, I would have assumed that would be that layering description would be a measurement that was taken as part of the boot process, as part of the attestation process, I guess.
The thing with the attestation process is that when you boot, you don't know which container images you're going to be pulling. So the model that Kubernetes provide is it starts a pod and then it can dynamically add containers. Actually, this is what it does. It even though Kubernetes knows upfront which containers are going to be running inside a pod, there's nothing preventing it from dynamically adding containers, or and there's nothing right now that Kubernetes provides in order for a Kata containers VM to know which containers upfront is going to have to pull.
So hang on a sec. If you're saying that, what stops a malicious host adding a malicious container after my pod has started booting?
Because I mean, the Kata agent is never going to run a container that is not being signed or encrypted, and with the key that get provisioned after attestation. So if as a Kubernetes control plane owner, you ask for a malicious container to be running there, unless it's something that's signed by the guest owner, it's not going to run in the container, in the pod.
So in that case, I think the answer to your layering metadata question is that layering metadata would be signed and that signature checked by the Kata agent.
The Kata agent doesn't know. You mean signed by the Kata agent?
Well, I mean checked by the Kata agent. If you're saying that the Kata agent is the thing that checks everything else inside the container, then I guess it could be the thing that checked any layering.
It does check in that model the layering and everything else. But if you pull everything on the host, then the Kata agent does not see it.
Right. So my suggestion wasn't to pull everything on the host. My suggestion was to pull each of the layers inside the guest.
Yes.
But to have the bottom layer be a shared layer, protected by something like DM integrity or something like that.
It's kind of a shame to lose the sharing aspects of containers and the trade-off of security versus shareability, especially if the common portion of the container stack is the huge portion. That could be integrity protected some other way.
The suggestion here are pretty interesting, where especially given that a lot of the container workload out there are sharing a fairly reduced set of base layers. But I mean, we need to think a little bit more about what it means to share the base layers and have the host seeing the base layers and being able to potentially tamper with it.
Not tamper. I mean, you're going to have it protected, integrity protected other ways, as opposed to just encryption, and move the whole thing into the guest.
Is that something that you can do per tenant?
So somebody talked about DM Verity is an option here.
But then you would need to have your OS provisioned with per tenant keys and being able to decrypt and verify base layers that are encrypted with any tenant that comes into your node. Is that right?
I mean, my understanding is that the way something like DM, I think it's DM integrity, I can't remember the exact name, works is it has some type of hash tree. So it's not actually encrypted.
Yeah, you could verifying and signing the layers would be a good step, but you need to be able to do that per tenant. As a guest owner, you want to make sure that something that comes from the host is exactly what you expect, and that's something that can be shared across tenants.
So the integrity part is one, and the confidentiality part is the other part, right? So by encrypting, you're making it not visible to anybody that wants to look at it. But what's the harm in looking at a standard Linux base image on which the container is being built? That image, we need to make sure it's coming from. We want to ensure the provenance of that image. Nobody has tampered with it. But allowing somebody to introspect that image is not going to really make a problem, create a problem for what we're trying to solve here.
Yeah, it is actually also a model. It's kind of a hybrid model where you would have a set of shared base layers signed, at least that could be on the host, and have an even more complex model than this one, where you would have some layers that are owned by the host or pulled by the host, and others that are in the guest. Right now, what we're doing is basically step 0 of that approach, where we put everything in the guest and move the entire image management layers on the guest. Because when you have this hybrid model where essentially you're going to split the entire image management layers between the guest and the host. So it's definitely something we need to look at. I think it's good suggestions, but yeah, complexity-wise, it's probably not something we'll reach with the first implementation for this.
Sure.
Okay, I think this is a good time to wrap up the discussion. I think we can continue it offline if need to be, or in the chat. Samuel, there are some questions in the shared notes. Maybe when you have time, you can answer them there or in the chat. Okay. So we're already running a bit late. So
sorry about this.
No, it's not your fault. So we are taking a break until 10 a.m. Pacific time, and then we continue. Okay, welcome back. So let's move on. Next is Mark, who will be talking about deploying CVMs at scale via Linux.
Okay, can everybody hear me?
Yes, I can hear you.
Okay, great. Thanks, Jörg.
Yeah. Now.
Okay, great. Yeah, so exactly like Jörg said, I'll be talking about deploying confidential VMs via Linux on our on Google's public cloud called Google Compute Engine, or GCE, and I'm Mark Orr from the GCE team at Google. Let me figure out how to navigate the slides. Okay, cool. So the TLDR of this talk is this community's made great progress on getting confidential VMs working. Today on Google Cloud, you can run just vanilla Sev, not SevES or SevSNP VMs. SevES is also supported by Linux today. And I'm very inspired by all the work being discussed today, and it's really awesome. So on my side, in addition to being interested in everything being discussed today and all the technical issues, I've also been very involved with trying to get some of this great work running on our public cloud. And I just wanted to take this time to discuss with you all some of the things that we've encountered. I've narrowed it down sort of to a very small number of issues, and depending on the level of interest, we don't need to go through all of them if there's a lot of discussion. So I've sort of ordered them in terms of the ones that I think are most important to least important. But TLDR is like merging code is not always enough to get this stuff working. There's things that need to happen after that. Yeah, so the things that I've decided to talk about today, and this is deviates a little from my abstract, apologies on that, because I realized my abstract that I submitted had way too many issues to go over. But these slides, I'm going to talk about guest image support, testing, and then host side KExec support. And again, if we don't get through all the issues, if there's lots of discussion on like the first issue, that's totally fine. Okay, so it should be pretty clear from the slides up to now that the guest image plays a huge, crucial role in confidential computing. And there's really two aspects to this. There's fixing bugs that are pre-existing in the images that we're offering to customers, and then as has come up time and time again with all these talks, whether it's like migration agents running inside the guest, whether it's support for lazy accept, so on and so forth. There's a lot of new functionality that's really exciting that we also want to that we need to get into images for customers to be able to use all this awesome work. And so this is just what I did. This slide, what I did, I just looked at all the images that on Google Compute Engine that are today tagged as Sev capable, which is a signal to customers that if you mark your VM as a confidential VM running on a AMD platform, that you can go ahead and enable the vanilla Sev. Again, no SevES, no SevSNP yet. And the thing to look at here is the current Linux tip as of last weekend is 5.15. And the images running on our cloud, and I assume other clouds are similar, are just much, much, much older. And so before we even get into new features, we also want to talk about bug fixes. Like we want to make sure the stuff that's working today that we claim works, that we can maintain it and fix it as customers encounter issues. And so I've sort of just focused on a very issue that that we've run into multiple issues on this setup during the past year. So looking at in Linux, you have a Linux guest side bug, and let's say customer hits a bug. We're not going to see their bug if encrypted, if confidential VMs are working as promised, but somehow we debug the guest, maybe using the previous debug presentation earlier, or maybe the guest customer gives us a repro that doesn't rely on any of their data, and we can run it and we can fix it, or however it happens, somehow we root cause this bug and we get it fixed. There's been an assumption, as far as I can tell, that we can sort of glue together pre-existing working components inside the Linux kernel and just assume that those will work together. But looking specifically here at this picture, on our cloud guest for the disk, they go through the NVMe driver, and then that confidential data is bounced through the SWIO-TLB component in the Linux kernel. So NVMe driver works, people are using that. SWIO-TLB has been around for a long time, that works. Some people use that as well, awesome. But we found a couple of interesting bugs in the last year, and our experience when we went to, I think at least my assumption was, oh, we have these long-term stable kernels. Turns out most guest distros don't base their kernels off LTS, but I assume that most guest distros watch what goes into LTSs because they want to pick up security and bug fixes. So my assumption was like, okay, we'll send the fix to the community, they'll take it, then we'll mark it for stable, and it will go to stable kernel, and then the distros will pick it up. Awesome. In reality, what we found was if the bug's straightforward and simple and all this, yeah, the community is great about accepting the bug, but we found a pretty complicated bug that related to the NVMe spec and how it required a offset into a page to connote information, and that offset was being lost in the SWIO-TLB, and it was a very complicated fix, and the community helped us a lot to get this fixed, and we're very grateful. Then when we tried to send it to stable, we got told, and rightfully so, hey, like nobody's ever used this way before. Why are you guys sending this to us? This is stable is all about making stuff that was working before, keeping that working, or fixing it, and it's not about introducing new functionality. And so, yeah, go ahead.
So I do have a question. If you can go back to the previous slide where you had listed all of the images that you had in your gallery.
Yep.
So have you gone ahead and hardened the VirtIO interfaces in these older versions of releases of CentOS and RHEL and SLES?
So maybe a little bit outside the scope of this talk, but we're not actually using VirtIO in our guest IO path. So we have not.
But you have bounce buffered the IO between the host and the guest. Is that what you're saying?
Correct.
Okay. So that patch actually went in and is available in all of the upstream kernels, or is it only in the private kernels that you have here?
It's available in the upstream kernels that are available on images that guest distros have made available to customers on GCE.
Yeah, because only recently, I think, we're doing bounce buffering work in the upstream kernel. And I see that you got really old kernels. So I'm surprised how you got the bounce buffering.
So SWIO, I mean, yeah, let's, TLDR, SWIO-TLB is a very old.
I get that. I get that. It's very old, but its usage in bounce buffering on the IO path, that's more recent. Usage.
Yeah, but although the headline kernel number there for CentOS and RHEL is prehistoric, in reality, the code we've got in there, certainly in a lot of the KVM paths, is much, much newer. Yeah. And we have tested SEV in some version number I can't remember. So, it's not the code involved in these paths isn't all that ancient.
Yeah, I mean, the TLDR is this is all working on our images. This was actually all enabled before I joined the team, so I can't go into the details on that. And even if I could, I think it's a little outside the scope of this talk, but this is all available on our images on cloud right now.
Sure. Thanks.
Okay, so that's guest side bugs. Again, the big takeaway here is like, how are we going to get these fixes to customers? That's what I want to drive discussion on. And then similarly, look at all the new guest side support being discussed today. It's just a lot of it. How are we going to get those into images? And so this is where I want to kind of back off a little bit and allow for some discussion. But I'm wondering my impression is that the big players are sort of one-off going to the big distros and sort of one by one, hey, can you get these patches in and so on and so forth. I won't name any names. That's sort of my impression. And I'm wondering if this can be done, if there can be a more efficient community effort here to get a set of agreed upon Linux images and distros that are interested in confidential computing to support a first class CVM based confidential image that will take these patches, we'll take the bug fixes, have a process to go that through, and so on. And so I'm actually going to be quiet for a minute and see if folks have ideas on this.
So from the SUSE side, first of all, when you have fixes for which are important for confidential computing, we usually look at stable patches, and what we also track is patches with fixes tags. So if you add fixes tags to them, they will get there will be email notifications to our developers, which will then look into it and see if it's important and backport it.
Yeah, that's been my working assumption. I guess from empirical experience this past year, we also need a process to get patches that are not necessarily accepted by stable, I would argue.
Yes, yes. So if it's an important bug fix, then we will likely take it. And with regard to a bleeding edge distro, so OpenSUSE Tumbleweed is usually up to speed on SCV and SCVES support. So that's something I regularly test. So it has all the necessary features and it can run as an ES guest. So if it's not too bleeding edge, then this can be used.
Right. I'm just wondering, like, what's the timeline on all this? If I go back to this, this slide, let's say we're at 5:15 now. So let's say some of this, let's say SMP support gets checked in at 5:21. I just picked a number. Maybe it'll be longer than that. I'm not putting any pressure on anybody. Like upstream, it goes the pace it goes, and it goes that pace for a reason. Does that mean we cannot run an SMP guest on a public cloud for 4 years? Because there's, that's.
No, I mean, there are established processes that are used to backport features to distributions. Yeah, and the amount of it is driven by each vendor. Like they work with the distributions, and they usually have a target and say, okay, and this is negotiated with the distribution vendor. The distribution vendor says, oh, I want to support this and certify it and test it by this release of the distribution, and the hardware vendor then talks with the distribution vendor and says, okay, yeah, we send you make sure the patches are in there, and we work together and test it and whatever. Yeah, so there's a standard processes. I mean, it's because it's not limited to confidential computing. Right? It's for every new hardware which needs some enabling.
Yeah, I see that's the same way, Sandy. Basically, things need to get on stream first, and then it's up to distro vendors to backport, and that's just like an OEM to distro vendor relationship.
It totally makes sense. I guess the question here is, like, is Google having to go off and talk to 5 vendors, and at the same time Microsoft's going off, and at the same time IBM's going off, and at the same time Intel is going off, and at the same time AMD's going off? Or can we establish sort of a confidential compute consortium?
Yeah, I think that there's already some work underway within the CCC to try to coordinate the efforts between the hardware vendors and the cloud providers that are going down this route of enabling this and from a software ecosystem perspective.
Yeah, I mean, the basic thing is still that every hardware vendor works with the distribution vendors. Yeah, is that wasn't like this? And just for the cloud, because they use virtual cloud images, there's usually like a second step where also the distribution vendor.
Andy, can you get a little closer to your mic?
Is it better? Yeah. The distribution vendor works with the and the cloud vendor, because they often produce like special images and stuff like this. Yeah. So I don't see this changing, because this is like the standard process which has been used for everything. Yeah? Because it is not just confidential computing. I'm not sure it makes sense to establish a new process just for confidential computing. Yeah.
So I think confidential compute has some difficulties in that it's fairly easy for us to spot things that need going into KVM, because we keep an eye on that from the KVM side, and we have good relationships with the CPU vendors for that as well. What is trickier is where your problem is in one of your device drivers or is in something outside KVM, we might not spot it. So I think it's good to be, if there was somebody who was gathering a list of patches that were needed for confidential computing, it would be great to have a list like that.
Yeah, and it's even worse because it's not only device drivers for functionality, but there's all this hardening work here. Because everything, even if something is working, but it could be a security attack. Yeah, right? And this makes it even worse because there can be a lot of patches. That's something we're experiencing, is that our patch kit is ballooning because not because we need that much for functionality, but simply we need to harden stuff and disable things. And most of it is just disabling stuff, but still it's unfortunately had this tank tackles all over the source tree. That's a disadvantage here.
And yeah, ideally speaking, right, I don't want to be saying that, for confidential computing offering on Azure, only these subset of images are allowed for customers to launch, right? I would like to open it up for, today there is no real restriction in terms of what image can be used in what VMs queue. But this actually is kind of bifurcating our gallery because of the hardening issues that you talked about and other kernel changes that we need to make to fully take advantage of the underlying hardware. That is not, I don't know if it will be available in older versions of CentOS or RHEL.
Yeah, I agree with you, but I mean, we want people to run everything they want to, right? But on the other hand, you have to be clear, and you have to be clear in your messaging that if people run something which has not been fully hardened and fully audited and fast, there's a security risk, and it needs to be clear to people that this is confidential computing with a K button and footnote.
And
yeah.
I agree with everything you said, Andy. But even before that, like not all images are going to be supported if they don't have the patches to do VC handler, to do GHCB protocol. So they're just not going to be supported. They're not going to work.
That's right. I mean, the functional enabling is the most basic thing, but then there's in addition this security hardening enabling. Yeah? This is another layer, another complexity. Yeah? But again, I mean, yeah, people can ignore the security part, but they need to be aware of the threats.
Okay. I don't want to cut off the conversation, but I want to move on to the topic. Is there any other last comments on this topic? Okay. Yeah, so let me go to the next topic, and Jorg, if we don't get to the last topic on my slides, that's okay in terms of managing time. And I do appreciate the discussion for everybody. Okay, so now I want to talk about like testing a little bit. At least in our cloud, I'm pretty sure other clouds are this way as well. We don't deploy a new functionality without tests. We just don't. And so I just wanted to talk with everybody about how we can get better about adding testing. And by the way, this is from our side as well. As I said, we run Sev today. We do have testing, and on our side, my team and my company has not done the best job always sharing our working in open source test frameworks. So that's something we hope to do better on going forward. But I also want to see the whole community do better on this. Oops, I keep pushing the arrow. Let me click. Okay. I'd actually had this slide animated, so it may be a little too dense to go through without the animation. But what I've got here on the left side is I've got a commit. This was actually submitted by us, and we did not submit a fix. So if I'm pointing fingers at anybody, I should be pointing sorry, we did submit a fix. We did not submit a test to go along with it. So if I'm pointing fingers at anybody, I should be pointing a finger back at myself. But I think this is something that we from what I've seen, we can all do a bit better on. So here, what I've done on the left side, actually, I've sort of taken the first 3 sentences from the commit that fixed the existing bug that happened when you'd exhausted all the ACIDs for the available VMs on your host, and then you tried to create one more VM, and it kind of got partway through the creation process, and then a command wasn't sent to the PSP to clean up some internal PSP state, and you can actually get the machine in a state where the PSP internally has had some resource leaked, and it will not allocate new VMs. Actually, without the animation, I think if I try to walk through this, it's just going to be too confusing. So the slides are on the website. You can read through this if you're interested. But basically, I just have a test that we probably should have written to go along with this bug fix that shows, step 1, just reading through the comments, exhaust all the ACIDs. That was to get into the condition of the bug. Step 2, exhaust all this internal PSP state. And then step 3, you should clean up so that you have ACIDs on the machine. And then you would expect to be able to create a VM when you get the machine back in this good state. But because of this bug, without this bug fix that's linked here, we couldn't do that. And so this is where I want to, let me go to the next slide. So this is where I want to get into the discussion. I'm personally more, have more background in KVM, not as much in like guest OVMF, not as much in guest images, a little bit from some of the debugging I've done last year, but I know there's been some recent exciting progress on KVM unit test for SEV, and I know that there's been some work on self-test is another framework for SEV. So I'd like to sort of highlight those efforts and get people more interested in reviewing those patches, first of all. But I think even more broadly, what other testing open source framework should we be leveraging? Going back to the guest image discussion, if a distro takes in, let's say we come up with some awesome way to tag all the confidential compute patches, and we figure out a way to get some distros that are accepting all those, how can we get some acceptance testing that distros can run after they've patched in those patches to make sure they haven't actually broken things? So again, I'm going to be quiet for a minute to facilitate discussion.
So the one which scares us a little as a distro is where you as a cloud roll out a change to your hypervisor, and then we find out the next day that none of our VMs boot. So I think we've got some integration with you guys somewhere for testing that, but especially with SEV, where life is hard to debug in those cases, being able to find out early before customers would be useful for that.
Okay. Yeah, I know how that's supposed to work, but our company's so big, I don't know that it always that things always work as they're supposed to work. So that seems like maybe something we can follow up offline. What's supposed to happen is we're supposed to run all the images plus what we're trying to roll out on the host side into a staging environment where no customers run, and have tests running that exercise this functionality. But if we're having gaps there, we should definitely follow up and get that fixed.
So should we be looking at having our friends in kernel CI take this on, CVM testing as a project, if you will?
Yeah, I think one of the things Mark's calling out here, though, is that we don't have any upstream tests that CI can run. And how do we prioritize getting upstream tests implemented and merged upstream so people can consume those? And how we balance that with new functionality, SNP, TDX coming along, where we have limited review cycles from maintainers to get all of that in.
I think it's already a good start to just run all your in-guest test cases you run on non-confidential VMs and start running them in confidential VMs, just to make sure that your guest kernel and your guest environment is stable and everything. You might want to spare out the performance test, or at least you should get another performance baseline for confidential guests. But I think that's already a good start, and then move on with the KVM unit tests for SCV and SCV-ES. Yeah, and the rest I think has to be implemented.
Any ideas?
Right, I don't disagree with any of those. How do we actually get that done, though? We have N number of weeks that people can spend reviewing SEV and TDX code. How do we balance the review cycles against TDX and SNP support versus all this test support and development cycles too?
I feel, Sean, part of the issue has just been that the patch that we posted for KVM unit test, for example, without it, it's really non-trivial to run a KVM unit test under SEV-ES. And I don't think self-test was as difficult, but I think we're in the same situation. So I am hopeful that once we do get this support checked into these test frameworks, that there will be more momentum and interest from other people outside the core hardware vendor developers for these features to actually contribute to testing and reviewing tests and so on. But maybe I'm not being realistic. I don't know what experience will tell us here in the coming months.
Yeah, I mean, one way to sort of, I guess, change up the priorities on things is, you know, a lot of things that are driving priorities is sort of on the business side, where sometimes the testing aspect kind of goes, you know, by the wayside or it gets deprioritized. This would sort of have to be a decision, I guess, at the maintainer level. But if, you know, if the KVM maintainer said, you know, we need this and this sort of tests in place before we accept these patches.
Well, another thing Michael, I totally see where you're coming from, and I've even had those conversations with other, like with Sean before I presented these slides. One of the things I'm worried about is there's already, if you look at the SMP patch that I've been slowly going through, and TDX I haven't read, but they're enormous patch sets. It's already a huge burden on the, you know, on your side, on the AMD Intel side vendors, and I'm worried about further serializing this whole process through these Linux developers. And I'm wondering if we get the support in the test frameworks, if others in the community could develop these tests in parallel rather than serializing everything through you guys, essentially. But again, I don't know if I'm not being realistic with that idea.
Yeah, I mean, I agree. It'd be great if, yeah, we could get more, parallelize that a bit. It's just sometimes that initial infrastructure that you need to sort of get those people in a place where they feel like they can make contributions sort of rests on that initial core development effort, and kind of, just doing that all kind of off on its own. Yeah, I mean, you just have to find the right people that are willing to take that on and are engaged enough in that early development that they can do that. So, you just have to find the right people, I guess.
Yeah, that's an interesting discussion. I think we have to wrap up now, but I'd like to continue that maybe in the chat, or we can meet afterwards in the hack room and continue the discussion.
That sounds great, York. I appreciate it. And
Great.
folks, feel free to read my slides for the last section. It was about KExec host site support. If folks are interested in that. And thanks for everyone's attention.
So the next talk is from Jim and James. I think Jim will be presenting.
That's right. I don't do any work. Yes. Can you guys hear me?
Yes, I can hear you.
Wonderful. Okay. All right. Ready to go. Let me just confirm how this works. There we go. All right. Hi, everyone. My name is Jim Cadden. I am from IBM Research. Yes? Oh, hi, Jim.
Saying hi, Jim.
Good to see you. I'm from the confidential computing team here at IBM Research, and today I'm going to be talking about the attestation and secret injection pathways of some of the work we've been doing over the last couple of years from my team. Particularly, we're looking at the AMD SEV technology and how to bring the feature to the IBM cloud as well as into the Red Hat hybrid cloud platforms. And but particularly, this is about the attestation story for confidential VMs, containers, and pods. So the AMD SEV confidential computing hardware provides, as well as the encryption of the virtual machine, provides methods for doing a attestation measurement, which allows the guest owner to validate the contents of the secure VM prior to any confidential data being exposed to the host, which is untrusted in this model, as well as a secure method for secret injection. And this allows, again, an external guest owner to inject a table of secrets into the virtual machine without the host or hypervisor being able to read or see the secrets. And particularly with regular SEV and SEV-ES, these methods come in the form of a pre-launch attestation or a pre-launch secret injection, where the measurement validation and secret injection takes place prior to the actual launch of any guest instructions. Secure hardware measures the initial memory footprint, which is our flash 0, and exports it via a secure channel to an external guest. The secure channel is set up initially in the arguments passed to the hypervisor. The external guest then validates this measurement against an expected value and can then return an accept with a table of secrets in reply. And again, this is coming back over the secure channel and entering into guest memory. The table in the standard approach comes into the EFI protected memory, where it then later can be read by the bootloader or the operating system. And important to note, the guest secrets are in a form determined by the guest owner themselves. These can be symmetric decryption keys, these can be API credential information, asymmetric keys to access the SSH endpoints, something along those lines. But a subtle and important point with this procedure is that the confidential components of the guest software must be gated by a secret. You cannot simply rely on a successful attestation stamp of approval in this model because there are attacks that would allow a malicious host or hypervisor to either falsify an attestation report or simply just ignore the request or the result of a guest owner and simply continue the virtual machine or continue the container, continue its boot. So the secret is effectively the key to start the confidential runtime. So in a regular model of just a virtual machine, the way this is done is with an encrypted disk. So the guest owner encrypts the full virtual disk of their guest. This is just a LUX2 encryption with QCOW. Now, QEMU, more recent versions support disk encryption through this method already, but by allowing the hypervisor to do the decryption and managing the key, we're breaking the trust model that SCD is providing. So we need a solution where the decryption and the key handling is happening inside the guest enclave. So in this case, the decryption key is passed in through the attestation measurement procedure. It's passed into firmware memory. We've moved the bootloader into the firmware, into the OVMF, so that it's part of the attestation measurement. And then that firmware is the one that receives the key, decrypts the root partition, and starts the guest. So these are patches that originated from our team at IBM Research in collaboration with the AMD SEV guys, and most of this functionality has been upstreamed into OVMF and QEMU, as well as I think there's an ongoing patch in the Linux kernel for this. Now, the story shifts when we're starting to talk about doing the same or providing the same type of protection as well as integrity verification with a container or a pod. And this is mainly because a container or a pod in the model of Kata containers is not providing a fully encrypted disk image, but instead the kernel and the initRD and the command line for booting the virtual machine are all part of the, or controlled by the host, part of the Kata runtime itself. And these files are not something that are selected or managed by the external client. So therefore, we need to find a way to bring these into the trust domain of the customer where the container is going to be deployed prior to the container actually being deployed or downloaded for that matter. So the solution we've come up with, and this is work done in collaboration with the Confidential Containers project that Samuel spoke about earlier. The solution that we came up with for AMD SEV was these 3 points here. The first was the hypervisor computes the hashes of the kernel, the initRD, and the command line at the launch time of the guest and writes them into the initial memory of the guest. These hashes are then contained within the attestation measurement, which is sent to the external guest owner to be validated. So this, again, prevents the host from manipulating the kernel or changing the initrd or passing anything unexpected in through the command line. If any of those things happen, the guest owner is not going to validate or not going to pass the attestation. And third step is that the firmware itself validates that the files passed in by the hypervisor are indeed the ones that match the hashes that the hypervisor computed. Because again, we are not trusting the hypervisor. The hypervisor could be lying about what files are passing in an unmatching hash. And this final step is that the OVMF, which is again part of the attested measurement, the OVMF is the one doing the final safety check here before the actual runtime is, or the actual guest is launched. And in this case, the guest is the Kata container agent, which in the previous talk we spoke about, the one is going to download the container image and do the unpacking. Slide. So, as I said before, the secret is the gateway towards actually being after the safety of the confidential information. So in this case, the secret table being injected as part of the attestation procedure. The secret table is then, in our solution, moved from EFI memory into a kernel reserved portion of memory. A kernel module included with the guest is responsible for now loading the contents of that secret table into a location where user space process can access it. In this case, we're using the security FS file system and modeling this with entries from the GUIDs in the secret table. Then at this point, the Kata agent that is part of the init procedure of the guest is responsible for downloading the container image and starting the unpacking or the decryption process. This Kata agent is talking to an attestation agent, which has been an attestation agent which has an implementation specifically for this SCV pre-attestation. So in this case, the attestation agent itself is just reading from this security FS file system in local memory. I'll talk about on the next slide how this attestation agent can be expanded to different attestation models. So in this case, like I said previously, the secrets can take many forms. We've imagined these secrets can be sets of keys for decrypting the layers of a container. We could also be using these as a secret for setting up a connection with a secure image repository, for example. It could be a allow list for containers to confirm that the container that is being deployed inside this guest is in fact one that is expected or one that is approved by the external guest owner. And finally, the piece of software which we're currently working on in this pipeline that is actively under development is this guest attestation agent. And the goal of this project in particular is to create a hardware or an infrastructure agnostic attestation component for the for the confidential container project for the Kata agent. So this would be responsible for handling the decryption key management for when a container, when an encrypted container is being unpacked inside the guest. So in this, we have a library called OCI Crypt RS, which is written in Rust, which is responsible for decrypting each of the container layers of the image that has been, of the encrypted image that's been downloaded. And this is this library is reaching out to a local attestation agent, which is running in part of the host, which is now the sort of the hardware dependent or the situational dependent piece that is either reading in local memory like security FS, or this is now the piece that in other attestation models like TDX or CV SNP is communicating to the external service and doing the attestation handwork and handshake and the key exchange at that point. And yeah, like I said, this is active development. It's under the containers project at the URL below. And that is that's the end of the slides I have prepared. But I have a little complicated diagram here that shows this full pipeline, and I'm happy to answer any questions you may have. Thank you. Let me read the chat.
Well, I think everybody agrees to the way we do attestation. Thank you.
Yeah, thank you, James. I'm trying to parse this chat, but it looks like it's a carry-on from the previous conversation. So I'm happy that that was a good talk. I'm happy that everyone's so engaged.
So one thing I don't understand about the Kata container ecosystem is I've seen different approaches to make confidential computing working for Kata containers. Will those coexist in the end, or will there be discussion to join the efforts? Or
so all of the conversations, at least today in this micro conference, we're all in collaboration on this under a same confidential container initiative. So the actual implementation design would be that your deployment of Kubernetes or OpenShift or just plain containerd with Kata containers, you'd simply just enable confidential guest containers, and then the system would recognize which hardware we're on, whether it's SEV or TDX or Z, and the correct level or the correct approach of providing the confidentiality would be implemented.
Jim?
Yes.
The workflow you have here in this slide, while it being described in the context of confidential containers, there's nothing here that says it couldn't be used for a CVM workflow as well, where I'm not interested in containers, but it's just an IaaS VM that needs to spin up in a confidential fashion and secrets being injected into that. Why is that not the focus as well of your effort?
That is the focus of the sort of the first generation of this work, is creating the sort of the infrastructure as a service model with SEV, and then how to do attestation and secret injection with that model, because it provides the same type of guarantees. This was the slide earlier when I talked about it with the Lux encrypted boot disk. And you're right, the procedure from a cloud provider perspective is largely the same, and the sort of the KVM in the sense in this graphic is the Kata guest in the sense. So sort of a layer sort of on top of this would either be the IaaS platform or the container platform, like a Kubernetes with Kata containers. But the actual exchange of files and information and secrets is the same.
Right. So from a distro vendor perspective, this workflow here in terms of how you provision a CVM image and customize it to a customer tenant keys, for instance, and then how we go about launching it, to the extent that the workflow of the launch impacts some of the pre-boot or boot components of the distro. It'll be nice if we can, collectively standardize on how this should work, because each of us is inventing the same wheel, and I'm not even sure if the way we are doing this workflow. I haven't looked at other cloud providers, but we do obviously have something equivalent of this today, and we are going to ask our distro partners to, plug into our workflow. And I don't know if each of us will go and talk to SUSE and Red Hat and Ubuntu to do something slightly different, because we have chosen to do these things a little differently.
It's actually worse than that, because potentially we have that for each of SEV and TDX. So potentially we have each cloud vendor and each technology multiplied by distros and possibly then multiplied by whether it's a plain VM or a container. So if we're not careful, the number of attestation mechanisms and startup mechanisms grows crazily.
It already has.
Well, but we can answer that a bit. I mean, if you look at this attestation mechanism, it works both for containers and for VMs. The only slight difference is you have to pass the secret up further for a container because it has to go into the guest kernel. Whereas for a VM, you pass it up to the bootloader and it then decrypts the disk. So I think we can at least unify that workflow for both Kata containers and for confidential boot. The next problem comes how you unify the technologies. And part of the issue here is that some of the technologies mandate secrets be done in specific ways. And there are possibilities that the latest generations of technology then become incompatible with this. And for those, trying to find a uniform overarching architecture is very difficult. We suspect we have one that will work for SMP as well, this diagram, but we haven't actually proved it yet.
Yeah, and everything that exists in user space, where you're doing in the open source, but I know at this point, we have an attestation agent. Intel has an attestation agent. Alibaba has an attestation agent. So there has to be some sort of consolidation as time progresses. But I suspect that will happen with time.
The biggest nasty is actually the attestation flows. They're all radically different among all of the CPU vendors because nobody ever thought of agreeing on them. So we have to have at least some agent, probably in user space, that knows how to do all of the attestations. And then we have to have agreement on how the secrets flow once injected. Because if you look at the injection mechanisms that are being proposed, Intel, AMD, and in fact everybody else is using different secret injection mechanisms. We're trying to rally everybody around the open source components we have, which is the firmware OBMF, the bootloader, either grub or direct boot to kernel initRD, in which case we need the kernel initRD to accept the secret, but it's a bit like herding cats.
So James, should there be a forum where we talk about, how we can herd these cats?
Jim will tell you about the Kata Containers Forum where this discussion is going on. Unfortunately, they seem to meet at very unfriendly times for the Pacific Coast, so I haven't actually been to any of their meetings.
I was more interested in on the CVM side.
On the which side?
On the confidential VM side.
Okay, so all of those conversations have been on the upstream mailing lists, but because we don't have a single list, they've been fragmented on, there's partly on the QMU list. There hasn't actually been anything on the KBN list of confidential boot because we don't need to modify the kernel, and the rest has been on EDK2.
Yeah.
This is sort of the problem we actually face with the whole of confidential computing. This is the nastiness of it. It's not really a separate area on its own. It's actually a stack threading problem. And that means you have to deal with all of the individual components of the stack on their own terms, which is why all of these conversations get fragmented across all the stack component mailing lists. In some ways, this is sort of something that open source technology doesn't do that well. Hopefully now we have the Linux confidential computing list, we can CC that list on all of these, So at least there's one single source to go to. But we then have this huge problem that if you look at the two lists I had to deal with, the EDK2 list is actually a closed list. So if I CC Linux Kokomo, then we have a problem that anybody who replies gets bounced by that list, and then that list gets annoyed and so on. You know the problem.
I think
when we first started this, the Kokomo list didn't exist.
I think this microconference is just some more evidence that confidential computing and this community is coming into form. So I think this is where these types of conversations can and will happen as the months and years go on.
A quick question from us. We have the confidential computing consortium as well, right? Wouldn't that be a place where to kind of put some of these questions, like the tag there?
Well, it's a bit corporate. We need something a bit more open source. I mean, it would be a place to house stuff, but the problem is not handing everything over to a different forum and then having them fix it for us. The problem is how we bring all of the current stack components into alignment and get them to agree on this particular threading model for the stuff we need to do. That's not really something that a confidential computing forum can help us with, because it's not the exclusive province of confidential computing, right? Because each of the stack components has their own separate considerations different from confidential computing.
I think Dave has something to say. Dave, can you unmute and make your statement?
You may not have a microphone access.
Okay.
Dave
No,
says
we can't
that
hear you, Dave.
the confidential consortium meetings are public and open.
Okay.
CCC. Yeah.
Right, but all that provides is another open forum. We still need to get people to the forum, and the more painful thing is we need to get people from the stack components to that forum. I can't see people from Grub wanting to go to a CCC meeting, or even people from QMU, although perhaps Dave would want to go. They'd go
James,
with.
I'm sure every one of the cloud vendors has a provisioning workflow and launch workflow for confidential VMs today, because we are about to go live with these things, if not already live with those features on our platforms. It would be kind of interesting to kind of show and tell what our workflows look like and how does it compare with Red Hats or AWS and Google, and see if there is some way we can come together in terms of not having to make separate requests to each of our distro partners in terms of how they should support our platform.
Yeah, I think so,
Oh,
sometimes.
absolutely. So I actually did the workflow for that on KVM Forum last week. So if you look at my KVM Forum presentation, hopefully will be on a video very shortly, it details the workflow of the IBM proposal for confidential VM boot of encrypted images.
No, it's not like, we're starting from green fields here, right? We've been working on this for a while, so we all have invested something here. So we should look at what parts, what's the best of what we have, and see if we can work there.
I think the main problem is, it's open source, so right at the moment, it's very new. We're chucking stuff at the wall and seeing what sticks. So having lots of different projects doing lots of different things isn't necessarily bad. We just have to come together after we finally agreed what it is we're supposed to be doing.
Yeah.
Right, and that's where we need sort of forums to help us with this. I think Matt Wilson was trying to say something as well. I saw him pop up.
Yeah, I was just trying to say that sometimes it makes sense to kind of sit back a little and see what is actually working in practice. And I think that that's worked really successfully in how the cloud started, and taking kind of a building block that everyone understands, like a virtual machine running in a cloud that has an API that you started. Like it was really just an extension of something that was already used successfully in practice, kind of in industry, to get useful work done. And we're still in early days here, so it'll be interesting to see the different proposals and what works and what doesn't.
Mm-hmm.
Okay, I think that's a good time to wrap up the discussion.
Great. Thank you, everyone.
Thank you too, Jim and James, for presenting. So I think we are running pretty late, but let's go over to our last session for today about securing trusted boot. Steffen, you're going to present.
Yes, thank you.
Sorry. Yeah, wait a minute, just to find you in the list here. You should be now a presenter.
Okay, how do I? Okay, awesome. Hello everyone, and also thanks Jörg for setting this up, and everyone's still staying for the last session. My name is Stefan, and I'm joined by Andras, and we're both working for a company called Decentric. And I think we're kind of wearing a different hat than most of the other people so far, because we are actually actively running Intel SGX in production for several years now. And basically in this talk, now with having access to especially SCV-SMP, right, we gave it a go and tried to kind of import one of our applications from SGX to kind of the new world, right, which is based on confidential virtual machines. And so we're not experts in this field, and that's why we kind of really want to get feedback on the current approaches that we have taken. Let's jump into why we're actually using confidential computing at a really high level, and basically it is all about enabling confidentiality and integrity of multi-party computations remotely on the cloud. So having kind of a really kind of high-level walkthrough, right? What's typically done is let's say a data analyst can define some level of compute logic that she or he is interested in, defines the data sets that kind of this compute logic or this query is run against. And then to a CC-enabled platform. And then we have one or multiple data owners that potentially could ingest data to build the foundation or build the leaf for this kind of computation. And what we now do here is basically that before any data owner ingests any data set, there's a full kind of CC proof of the environment. And that really means like we do a full, the client is able to completely verify the trust execution environment that this is running in, and also kind of completely verify what is the compute logic that is being applied here, right? So this is not only kind of what has been ingested here, but really the complete TCB, and in that case is running in SGX, and it is being kind of measured here, right? And the client attests to whenever there's an interaction. And we also use an attestation to then establish a secure channel such that the data owner can ingest the data set, and then the computation can be executed, and the results again passed to the kind of original data analyst. And you see we need a couple of unique guarantees here. I think most of them we already touched or talked about today a couple of times. But in our context, code auditability is really important because, as highlighted, the data owners in that case should be completely able to kind of audit the code, understand what is kind of the logic, compute logic that's run against their data. And due to this kind of, auditability is important, but with that also attestation, right? They need to verify that exactly that code they have audited is really running also remotely. So we have a large focus on kind of measuring the workload, right, and adding that to the attestation flow. And last but not least, code flow integrity is really important, because with the kind of SGX technology so far, which are application process-based, most of this is custom, and we can quite well kind of understand how the code, what is the code flow happening here. But obviously, and we will talk about this right now with VM-based, the code surface is much larger. We put in software that has not been developed for this purpose, right? And kind of we need to take care of this, right? And these are also the two topics you want to dive deep in a little bit, starting with the attestation. And basically what we need in our case is measured boot, right? So there's no secret needs to be injected. We don't want to hide any of this. It's kind of plain vanilla, trusted or measured boot. And so basically the projects or the proof of concept we have done using the hardware so far is are quite simple ones here. Basically the first one is just fusing everything together, right? The firmware, the NVMFS, the kernel, the command line, and then kind of measuring this at VM launch, and then the user can attest to this before connecting. This comes with a couple of problems. I think first one is that's kind of it gets a bit hairy with like baking in the entire image into the original firmware with some hypervisors, but also we need to path this entire block through the secure processor, so it can take some time. And so basically one easy way to fix this is like adding one level of indirection, right? A hash chain basically where in the firmware we can now bake in the expected value, and during booting during the firmware, we actually are just asserting that whatever is being loaded here is the expected value, and only this checks out kind of control continues, right, and that's passed on to the kernel. That's not ideal either, because that means whenever anything changes in the kind of kernel RAMFS, we need to update the firmware, which is not nice. So ideally, we would do this a bit more dynamically. I think one way to do this is add some notion of isolation namespacing here, which would be this allows it to kind of a chain of this attestation flow, which VMPL could be used for. I think generally really nice would also be some kind of PCR-like scoping, right? That allows you to get this monotonicity in. Or I just heard actually of Jim, I guess, from IBM, that there's also a way to pass it through from the hypervisor and then add a attestation report later, basically the expected value, and with this push this to the client to do the assertion here. So basically, with this measure boot, we're kind of, I guess, feeling comfortable with like the options. But now the big question is really, what is the firmware and what is the kernel that we're booting here, right? And with that, I will actually give it hand over to Andras.
So the firmware, the obvious pick for the firmware is OVMF. We have tried a custom firmware as well, but we're realizing that really the community effort is behind OVMF, and Intel and AMD are both submitting patches to OVMF, and there's very special code that needs to be run to actually enable computational computing. So and we don't want to basically maintain our own stack for this. So we actually did a POC using OVMF, and actually the previous talk, I think we used most of that work. We extended it a little bit, so we added in Grub, we added a way to assert the measurement of the loaded EFI image, and we used like a unified kernel image as the EFI image, so that contains the initRAMFS, the kernel, and the command line. And then basically in the Grub configuration, you can assert the hash of what you're loading. And one of the things that we realized during this POC is that it's actually very easy to trigger a rescue shell in Grub if you're a malicious hypervisor. And then we realized that actually there are all these different ways that the hypervisor can influence the control flow of the VM. And sort of our big problem statement and questions around this, and I think a couple of talks actually mentioned this, like how do we actually go about securing all these different ways the hypervisor can influence the VM's control flow when using existing software like OVMF or the Linux kernel, which were not written with malicious hypervisor in mind. So there are a couple in the picture. You can just see a very crude representation of a control flow graph and the different ways that information can be injected into the VM. Like at the very beginning of the VM launch, we already have parameters passed into the VM from the hypervisor, which is coming from an untrusted land. Things like the memory map or ACPI tables. How do we actually secure all this? We need to guard against malicious virtualized devices, a couple of days ago, I heard about option ROMs, which I didn't even know what those were. But basically, you plug in arbitrary code. Basically, you can inject arbitrary code into the VM through that. So it's we have all these features that were developed for OVMF and the kernel, but all those features suddenly become attack vectors in the confidential computing realm. So,
yeah, so for the Linux kernel, like I talked about earlier, we're disabling all of this. So we have a lot of patches, and for PCI, we basically removing all the features apart from the most basic here. Like there's so many, you're right, there's so many features and all kinds of weird stuff. Yeah, but PCI is only the tip of the iceberg. There's also lots of other things. Yeah, it's a pretty big attack surface. So the key is really to minimize, and then the rest has to be audited and fast. Yeah.
Right. I mean,
sorry.
So one thing that I noticed is I think there are actually different kinds of use cases that people have for confidential computing. One of them is to take existing operating systems, existing distributions, and try to make it secure, sort of. And we come from different background where we really don't need any of those features, right? We just don't need those drivers. We don't need anything. What we really need is the bare bones byte stream in and out of the VM, right? And like VSOC, for example, is a good abstraction for this.
No, but sorry, even the standard distributions don't need the drivers, yeah, because they're nearly always for features which are not available in a guest. So I don't think your problem is that different from a generic distribution problem. Yeah.
So is there a coordinated effort that is trying to cover these attack vectors?
I mean, I would say it's an ongoing process. I mean, we're doing a lot of work on the kernel, and there's work on the firmware. I think that you should probably go to Eleanor's talk at the security summit. She's talking about this more. Yeah.
I mean,
I think, yeah. So
sorry,
I think currently grub is kind of missing. So nobody's working on grub, and grub is a big mess because there's not a single grub, but a zillion different forks. But other than that, I think that there's ongoing work here.
Hey, I've been working on grub.
I mean, I've also one like a feeling like obviously, and I think that also has been talked before, that it's a lot of work to enable all the different like hardware kind of vendors, right? So with the different technologies that we're also having, and it kind of makes sense that kind of, I guess, from the hardware vendor, they pick OVMF because it's kind of the most mature project and allows everything, right? Kind of boots Windows and stuff like this, right? But I have the feeling now we have this gap, right? That other projects, and I've seen also the talk from Sergio and Lipke around and so on, really wanted to have something like a really minimal firmware, like a really stripped down firmware, right? Where none of the stuff exists. We don't need shell in there. We don't need all this like EDK2, like all of this, but not all of this should be pulled in, right? And however, that leaves us with the fact that kind of we need kind of all of this work needs to be done again, right? We need to like on a separate firmware. Like, so we have two options, I guess. Either take OVMF and find a way to really strip that down, or kind of agree on a like it's Qboot or Rust firmware or whatever, where kind of all of these kind of hardware primitives are being implemented.
I mean, the way I see it is, often people look at just the code size, but the code size is not the right metric. The right metric is how many communication points you have. Like for example, it's the same analogy with a network server. You don't care how big your network server is, but you care about is how much communication does it have with the outside. Yeah, I think the trick is that that's the approach we had is that we take an existing code base and we disable things which we don't need in the existing code base. But for the other things, I mean, for a lot of other stuff, you can't basically say, oh, you can't just have like, kind of like a firewall. That's the approach we had, right? So let's say, oh, if we have megabytes of codes in the firmware, yeah, it's only attackable when it does MMIO or PCI conflict-based read or things like this. Yeah, so communication points. So if you can secure the communication points, and have a low list there and so on, then you can. It doesn't really matter how big the code base is. Yeah, that's because that's the only thing that really matters. Yeah.
So making it concrete, just as again we're kind of newcomers to that space, like we don't actually need grub, right? Because we don't have encrypted and disk we want to like load here, right? And so actually that was just for convenience. So is there anyone kind of familiar with an effort that we can kind of join or contribute to that kind of takes OMF and tries to like really strip away all the things that are not needed to run a minimal Linux kernel?
So the OVMF and grub is not really needed even to boot a Linux kernel,
Sure.
right? So Linux already has support for direct debooting from
Exactly.
Yeah. So this can be just used. However, the problem we had is that there were various distributions that showed us out they still want grub for some functionality or for commonality. But I mean, if you don't care about having a standard distribution, then there's no need for grub at all. Just boot it directly, build the kernel with the EFI step, and you're good.
Exactly.
But I mean, you still have to secure the firmware.
Actually,
right? And the kernel.
there's a problem there. In what you propose, if you use grub, you can have the encrypted envelope being the entire VM image. If you want to boot directly to the kernel has to be accessible to EDK2, to OVMF. OVMF can't read our encrypted file systems. So something has to bridge the gap or supply the kernel from outside the encrypted virtual machine. And this is sort of contrary to the way we currently use VM images. It's just one of these annoying threading problems that keep occurring in confidential computing.
Yeah, I mean, so this is actually one thing that we wanted to comment on, that our use case actually doesn't require encryption of the disk at all, right? Encryption of memory is sufficient. We don't want to protect that we are using like a Linux kernel with this application logic, right? There's no secrets in there. All the secrets are provisioned dynamically once we attested the actual software hash. So this is why.
Sure, you still need authentication on the disk, because if an attacker can randomly change your user space, then obviously you cannot do anything securely, right? So even though, I mean, you don't need encryption, but you still at least need some kind of hash scheme or something.
So we
need to measure it, right?
Yeah.
Yeah, measurement is needed, totally, right? I think it's more about like really, are we able to read from a LUX to kind of encrypted kind of image or something like that, right? Which is obviously a bit more like important than kind of computing a hash when you map in.
And in our standard TDX model, what we had originally proposed was, you just have an unencrypted partition, which can be read by the OVMF, by EK2, and it contains the kernel and not encrypted, another innerly not encrypted, but they then are tested using the attestation protocol. And when they are attested, then they can be executed. And this way you don't need any grub, because the EDK2 can do it directly. Yeah.
But still, like maybe a question, like I'm still wondering if anyone kind of worked on like what there are these weird cases, right? And when you're at the right moment mount a disk or something like that, right? Suddenly you end up in this EFI shell or stuff like this, and you can do whatever you want, right? And you're kind of, especially your VM launch attestation is out of the window, right? So I really still think we should, even like taking grub out, even OVMF, I mean, at least seems to be, if you just tinker around with it a bit, has a lot of features that can be abused really easily.
I think you should have a look at libk, right? I see Sergio wants to say something. He's actually the author of it. So Sergio,
can you hear me?
Yeah.
Yes.
Sure. Yeah, but so basically that's I think that's lick-around approach basically. So the idea what lick-around does, well, originally it simply loads the kernel image into the guest memory, but of course with SCB you cannot boot directly into the guest because you cannot set the page table directly from the VMM. So what we did is build a very, very small firmware that's just the bare minimum needed to set up the environment and jump into the 64-byte entry point. So yeah, that's all the features that the firmware provides.
And that's based on Qboot, right?
Yep.
So, and would that mean like, I mean, obviously that's now like, now there's SMP support, right? There will be TDX support. I guess that's what I was also the direction I would have like driven the conversation. That another option obviously would be to just take a really minimal firmware like Qboot and try to make sure we have kind of all of these security related and relevant primitives also there as well, right? And it seems like you guys have started this. Is this kind of a commitment to kind of a long-term support, or how would you see that?
Well, to this point, this is mostly an experimental project, so it's hard to make any long-term commitments. The good news is that we've tested so far up to SEB SMP, and we know that we can get away with doing very little to get into putting the gas kernel, so that's great. We're also experimenting with some other stuff, such as not needing to communicate with the hypervisor for anything at all, not even for obtaining the amount of RAM or the number of CPUs, and having that information also injected by the attestation server, so to keep the communication channel as minimal as possible. But yeah, that's basically it. The good thing is that in the end, there is not much code to maintain because there is not much code at all.
In Qboot, you mean, right?
Yep.
Yeah, no, that's
especially in the stripped down version of Qboot. I don't remember the exact number of lines, but it's very small.
But so usually implement things like this, like GHCB protocol and like weird interrupt handlers and like basically
just the minimum. Okay. Yeah, just the minimum needed to put. For example, the last version has support for the BC handle for the BC exceptions, just to be able to boot SEBES properly without hard coding the CBit. But yeah, the idea is to just add the minimum to get the kernel up and running. So the idea is not that the firmware doesn't need to have any entity by itself. It's just a way to start the kernel, which is we are interested in.
No, exactly, and I think we are as well. Like, and my last question, like for example, like the parameters we usually get from pass it via firmware config. I guess that's not part of it anymore, from what I've seen, at least from the code. But did I understand this correctly? That like memory layout, like all of these things we listed there, the parameters usually pass in. They're kind of propagated through the attestation, or like how do you now deal with these kind of configs that we need to provide somehow, right?
Yeah, so basically the thing is that for the SEB and SEBS model, those parameters are injected as part of the secret. So the secret is for a 1-page long, so you can put wherever you need that. Yeah. Another more radical approach will be to have the attestation server to provide the firmware, which is not that large by any means. It's like 64 bytes. So yeah, it's something that is 64 kilobytes. So it's something that is doable. And that way you will provide a custom firmware for each VM, which is of course an extreme approach, but it's something that's doable and it's interesting and maybe worth exploring.
Oh, okay. And I mean, I think what would be really nice also is, and I'm not sure if anyone like of the kind of AMD maybe later on or TDX thought about this, like that we have a similar model like we have with like TPMs, right? That we could just put all the parameters in the first PCR register, right? And like have this kind of monotonicity that we can leverage here. I think right now this will be still really hard to do, but yeah, I think that would be kind of an interesting approach as well.
Okay, so I think this is a good time to wrap up the discussion.
Yeah, thanks a lot, by the way, for everyone participating in the conversation. Thanks.
Yeah, thanks for your session. So I think we can move on the discussions to one of the hack rooms soon. But before we close the confidential computing microconference, let me thank the sponsors again. Without them, this microconference and all of the Linux Plumbers would not have been possible. So first of all, Facebook is a diamond sponsor, and IBM is a platinum sponsor. And also, of course, ARM and Microsoft as the gold sponsors, and the silver sponsors, Amazon, Netflix, and Red Hat. Collabora as our speaker gift sponsor. Thank you. And VMware as our t-shirt sponsor. Thank you as well. And last but not least, of course, many thanks to the Linux Foundation, who is providing the conference services for Linux Plumbers.
Jörg, how do we get VMware t-shirts?
I have no idea. I suggest, from what I heard, I might be wrong.
I can tell you that. So yeah, the t-shirts will be mailed out. You can't give them to you, obviously, to the first 200 people who fill in the closing survey. So there'll be a survey announced at the closing. So if you don't attend the closing, you won't get the link, you won't get a t-shirt. And if you do attend, you'll get the link, and the first 200 people who fill it out will get t-shirts.
Okay, I'll be sure to fill it out. Thank you.
Okay, thanks everyone for participating. I think we had some great discussions. And maybe we can continue them now in one of the hack rooms. I see hack room 5 is empty, so maybe we just gather there and continue the discussion there. Thanks, everyone.
Bye, everybody.